All right, welcome. We are now live on YouTube. Welcome to the second day of the 11th OPTICON Gaia Science Alerts Workshop. And without further delay, I let Simon Hodgkin to chair this morning's session. Simon.
Hi, I'd like to chair very light, but we've got a lot of 15-minute talks to get through. So I'm going to ask the speakers to really try really hard to stick to their allocated time. I'll try not to interrupt, but if we're really getting close to the time, I'll cut in and give you a warning. Otherwise, I'll keep stumm. And let's have Pavel take it away.
Thank you, Simon. Hello, everyone. Give me a minute to share my presentation. Okay.
I see screen sharing, but no slides, Pavel. Ah, there we go. Now I have slides.
Yeah. And what about now? Are they in the full screen mode?
The full screen now, yes.
Okay. So I'm going to tell you about the spectroscopic classification of our set of microlensing event candidates. And I would like to start with the OPTICON follow-up network, because many of you are the observers involved in the OPTICON time domain astronomy follow-up network. And mostly you do the photometric observations, but also the spectroscopy is possible thanks to observing time, which is awarded by us based on the proposals we're writing, or thanks to some colleagues which are involved in this network, and we have easy access to spectroscopic instruments as well. So this project can be done thanks to a collaboration with many people, mostly observers and data reducers. So we, all of you are involved in this collaboration. So thank you very much for your support and your data. Based on this, we are able to do the analysis, and we're able to get the results I'm going to show you in a moment. So what is the motivation? The motivation is simple. The idea behind this is simple because we are interested in microlensing events, and we are looking for black holes as lenses in microlensing events. So we want to distinguish the microlensing events, true ones, from the other types of variables, outburst, flares, young stellar objects, BE type stars, Myra type stars, and so on and so on. Because Gaia alerts are usually not classified automatically, as Simon have presented yesterday. 25% of Gaia alerts are classified by alert type. So for the rest, we don't know at the moment of the alerting detection. We don't know which kind of target we are looking at. So here are the examples of Gaia light curves for 3 different types of objects, transients. And at the moment of this black point, when Gaia is alerting about this transient, we we are not sure if we see at the microlensing event or this rise in the brightness is based on something else, for example, outbursts or flares or some other variability. So we want to select the sample of such events like this one at the bottom of this page. And then for this, only for this object, we would like to invest the time in OPTICON follow-up network to continue the monitoring of these targets. For the most interesting targets, we are able to do some more detailed analysis. You will see some results in a moment. So at the moment we use many telescopes. So for example, for low resolution spectra, we have obtained data from 10 meter SALT, low resolution spectrograph, 2 meters Liverpool telescope, and the Schematic telescope located in Azerbaijan. We also have some observing time on 2 Geminis, and we are able to get the spectra from GMOS north and south instruments. So these are the examples of the low resolution instruments in our set of instruments. And for high resolution, we typically use VLT X-shooter, which is excellent, not only because of the resolution power, but also because of the wavelength coverage. It's really long spectrum in the wavelength, which helps us a lot in our analysis. In last year, we also gathered some data from 1 meter Las Cumbres Observatory Echelle spectrograph. There are 4 of them, as far as I know. And also we have obtained a spectrum from Pepsi instrument, which is mounted on a large binocular telescope in Arizona, in the US. The resolving power is great, up to 250,000, according to the website and manual of Pepsi instrument. But of course, it depends on the weather conditions and the settings, and also depends on the magnitude of your target. In total, Gaia detected 344 microlensing event candidates so far, and we have collected spectroscopic data for 161 objects, and at all. So that means that we have microlensing event candidates and some other variables which are not microlensing events. So these are the numbers for which we have got a spectrum, and the plots shows the magnitude distribution of the targets for which we have a spectra. We have spectra. So as you see, we have obtained data for many targets between 12 and 19 magnitudes in G band. And this is on the right hand side is the plot with sky position of our targets for which we have obtained spectra. So usually we are focused on the galactic plane, but sometimes we see some interesting event outside the galactic plane. So these are examples for low resolution data, and they are good enough to classify Gaia alerts based on typical absorption or emission features. So based on that, we classify, we divide our sample on two groups, microlenses, which are normal stars, like this example of the GMOS spectrum, and non-ULens, microlensing stars events. Sorry, these are the examples of non-microlenses: B star and some young stellar object with prominent emission in H alpha line. So so far, 18 ATLs was published based on that. And for the sample of our microlensing candidates, we do the we ask for the observations in high resolution mode in order to do the absorption line analysis, and because we want to determine the parameters, effective temperature, surface gravity, metallicities. And this is the example of X-shooter spectrum for Gaia 18 AJZ, the blue one. And the red one is the synthetic spectrum, which is overplotted on the observed one for a specific set of parameters. So based on this analysis, based on Kuruc and Marx models and the different radiative transfer cones, we were able to determine the parameters which yields to other physical parameters like radius, masses, and together with absolute magnitude extinction, we can estimate the distance to the source. In order to obtain extinction values in the direction of our target, the matching of obtained spectra with templates is necessary, and Etienne Bachelet does this analysis. So here we have an examples of X-shooter spectra at two different epochs, the blue and the orange. And the models with extinction fits pretty well to this observed spectra, unlike the models without extinction implemented. Such analysis delivers us the values of the extinction. And now I want to show you some interesting cases. So at first we have our old friend, Gaia 16 AYE, for which we have obtained a set of low-resolution spectra from Liverpool telescope, from Asiago and Palomar observatories. And based on this very nice set, we were able to study the spectral evolution and to check the changes in the spectral features. We haven't seen any dramatic changes, just the flux density changed because during the evolution of the microlensing event. We
2 minutes, please, Pavel.
Yeah, sure. Okay. So we get some high resolution spectrum from Isaac Newton telescope and determine the parameters based on which we know that the source is a K5 giant at a distance of 10 kiloparsecs from the sun. And these results are published already in the paper last year. So it was a spectacular binary microlensing event. Other interesting case is a metal poor giant. We also got some spectrum from X-shooter, and we did the analysis in the same manner, but we also studied the kinematic properties. We calculated the space velocities in the galaxy UVW and the maximum separation from the galactic plane, and taken the selection criteria from Ibukiyama and Arimoto. We divide our galaxy into these three parts: thin, thick disk, and halo. And it seems that our metal pool giant is located in galactic halo. This plot also confirms the trend, well-known trend, that the old metal pool stars move faster in the galaxy than the others. And the last one, Gaia 19 BLD. You will have more about this in a presentation of Chris Rybicki. Based on high-resolution spectra from X-Shooter on the left side and on the LCO shell spectrograph, we classify this target as a giant at K3 type star at a distance of 8 kiloparsecs. And here we have a matching of the X-Shooter data and LCO data with templates, which yields extinction values. And this was submitted already, and this paper is in review. So soon it will be publicly available. So that's all. Thank you for your attention. I'm happy to answer your questions. I hope I'm
Thank you very much, Pavel. Very nice. Very good work. We have time for one very quick question from Guy Rickson. If I can call on you to ask your question, Guy.
Yes, I was wondering, how accurate is the distance determination from the extinction? And how much does it improve things if you have a Gaia parallax for the target?
Well, yes, it depends. It depends on the quality of the magnitude measurements and the method for which the extinction and absolute magnitude will be calculated. Because if, for example, in the case of red giants from the clump, we have a quite big, they are located in the HR diagram, which in a very complex region, right? So the small changes in magnitude imply on the big changes in the distance, for example. So it really depends on the quality of the parameters. And your second question was how the Gaia parallaxes can help us in this matter. Actually, for many of the microlensing events, Gaia parallaxes are not reliable because of the blending light and the movement of the photocenter, let's say, of this system. So sometimes our distance estimates agree with the distances obtained from Gaia, but in many cases the values are different, and that's why we rely on the spectroscopic analysis instead of Gaia parallaxes in that case. Yeah, because the parallaxes measurements are not reliable.
Okay, we're going to have to move on. Thank you very much, Pavel.
Thank you.
Next, Gabor is ready to go, Gabor Marton. And Gabor, I'm going to, when 12 minutes are up, I'm going to warn you, you have a minute or two left, depending on how many questions you'd like. So it's 15 minutes, including questions. Okay, thank you, Gabor.
Thank you. So hopefully you can hear me.
Yes, I can hear you very well.
Right. So the original title of my talk was Classification of Gaia alerts with Machine Learning Algorithms. But after I had a look at the agenda, I realized that maybe it's not the best one because there will be a lot of presentations about classification into different type of objects, but this is not the case here. So I think I can change it to eyeballing of Gaia alerts with machine learning algorithms. So it describes more accurately what is happening here. These are the topics I want to cover, but since we have not so much time, I'm just skipping to the next slide. So this is what Simon showed yesterday and explained in details how from the raw data the pipeline goes into the published alerts, and there was this wet neural network, which is the brain of the voters, and that's what we basically want to replace, or at least help the voters to decide which alerts are going to be published and which are not so interesting. So the question is, of course, how the humans decide which alerts are interesting enough. There are a couple of figures to help these people, including me sometimes. But yeah, so you can see environmental plots, light curves, and so on, goodness of its plots. But of course, there are many other things you may consider, but these are for a big help in the work. And this is how the voting system works. So if you are very sure that something is interesting, you vote with a yes. It gives a score of 1. Maybe you say that it seems to be interesting, but not that interesting, then you can vote with a yes. That's 0.5. And fortunately, there is I have no idea option, which is the don't know. It's a 0. And there is 0, -5, and for the definite no, it is -1. So the total must be 2 or higher to publish. So you can see that it's at least 2 people need to be involved in this process, but sometimes there are disagreements. So even more people have to vote and devote their time to this voting system. From this plot, you see that, yeah, actually there are 3 people voting, Simon, Diana, and Delme. They do the majority of the work on a regular basis. So from the core team, it needs a lot of effort to publish the votes and to publish the alerts and to vote. So it would be nice if the voting was a bit automated or fully, and they have more time for science or other parts of the work. So these are the methods. Just quickly, I want to go through what are the options. And basically, the only option is machine learning, because it is everywhere now, literally. So in the cars, TVs, phones, websites, washing machines, whatever. So really everywhere. And the point here is that you can calculate some numbers, parameters, features, whatever you call, for yourself, or you can use images. And all these input data could be used with several methods, like decision trees, or projecting them into hyperplanes and find the decision boundaries, or different kind of networks, or clustering analysis, and so on. But the question is that, can the machine differentiate between published and unpublished alerts as humans do? Here I'm showing an unpublished and a published, and I'm quite sure that you can differentiate and find out which one was published, but I don't tell you. So I'm going to start with this method called PyTorch, which is using images. So it's using convolutional neural networks. And the idea to use that was coming like 2 years ago, when there was some problems with Facebook, and it was not showing images, but it was showing the labels. So it was like, image may contain night, sky, and outdoor. And yeah, it's also pretty scary that how many things can be learned from images for machines, and how efficiently they can identify different objects and so on in images. So it's an open source machine learning library developed by Facebook's AI research lab. So you know that this is developed by professionals. It has different interfaces, for example, Python and C++. And because it is a professional thing, it uses tensor computing with strong GPU acceleration. You can run it on many kinds of operating systems. And also, you don't need to build your own CNN models or own convolutional neural network, because many award-winning networks are already implemented. And if you don't need it for a long time and you just want to play around with it, you can still use it on the Google Colab with GPU acceleration. So yeah, these are the images that we basically use in this exercise. And yeah, 40 images, including 16 plots, not in all cases, but we have 4 types of detectors: the old source delta mag, mean RMS, new source, and old source skew von Neumann. So you can imagine that how many tests we can do and how many tests we already did during the last year. Also, if you don't want to use images but you want to use parameters, you can calculate quite a few ones. So there are like 19 features for us to describe the environment and some basic parameters of the light curves, but also you can use other packages. In this case, I use the feats Python package to calculate the features of the light curves, 34 features here. So in total, because there is some overlap, you could use 50 features just to identify if something is interesting enough. Yeah, I'm at halftime if I'm correct. So here are the results. Just highlights of the results, of course. So I'm going to show that basically in this image, the first plot, which is the light curve, it seemed to be very useful to classify the mean RMS and the delta mag detector alerts. The third plot, it was useful for the new sources and also for the mean RMS. From this image, it turned out it's not that helpful, but still the delta mag values, the delta mag kind of alerts were classified with high accuracy, above 90%, using the goodness of fit plots. Also, the environmental plots seem to be useful for the new sources. And it basically describes the reality, because the environment is very important for this kind of alerts. Another type of environmental plots, again, for the new sources, it seemed to be very efficient, not so efficient in other cases. Here are some confusion matrices, just to go a bit more into the details. Of course, here you can see the true label, the predicted label, and for the delta mag, you see that in 94% of the cases, it was classified into the good category for the published. For the unpublished, it was close to 91%. So here you can basically decide if something goes wrong and you cannot get any better results, that you go for the completeness, which means that the unpublished ones need to be a higher score. Then you will not publish many garbage. Or you can go for the accuracy, but you will lose a lot of the interesting ones. But yeah, in case of this skew von Neumann, you see that the unpublished were identified very well. But if we go with this kind of classification, we will lose a lot of the already published ones. But still, it means clean, that it remains clean in our case. So these show the accuracies for the random forest classification, where we use the numbers, features, parameters. If we use the environmental plots only, you can see the results are not going really above 80%, and this 80% is achieved only for the delta mag kind of alerts. But if we attach the light curve parameters, we can go easily above 90% accuracy for most of these alerts. Skew von Neumann, of course, is a different kind of animal, and we don't have much data from these kind of alerts because it was introduced not a long time ago compared to the other ones. Also, you can see here what were the most important features. I don't want to bore you with the details, but yeah, it's easy to visualize which features are the most important for the different kind of alerts. It will hopefully help us to reduce the number of features used in the classification, so it can speed up the process a bit. And here is a comparison of the best results achieved with PyTorch. I also included it here, which plot was the most useful. And this is the score, the accuracy coming from the random forest approach. So you can see that the numbers are almost identical. So it is good news because we can choose which is the better in terms of processing speed, or we can also decide at the end to include both probabilities coming out of these methods. So maybe the users can decide at the end which they believe, which they trust more. And of course, the last slide is about our future plans, which is, yeah, to finalize the model, implement the code, and test it on the new alerts. And yeah, it's not really working for the first time, usually. So we need to finalize, implement, and test again for a few more times, but hopefully not for a long time. And we can really implement the last and working code. And then Simon, Diana, and Dami will have a lot of free time on their hands, and we will enjoy the new alerts without the voting system. So that's all. Thank you.
Thank you very much, Gabor, and thank you very much for sticking to time. So we have time for a few questions. I remind you, either using the reactions box, you can put in that you have a question by raising your hand, as I've just done, or type a Q in the chat, also works to everyone. I do have a question I'd like to ask, and I'd like to gauge audience reaction as well as Gabor's reaction. So what I think you're suggesting, implying in fact, is we could publish more candidates, but each candidate could have a probability associated with it as to whether the eyeballing team would have liked it or not. That's all we can say. I must say I'm surprised that eyeballing team, or rather I'm surprised your machine works so well, given the eyeballing team don't agree with each other necessarily terribly well. And that may be why you have some sort of differences, especially in some of the detectors. But I'd like to hear from people if they think a more noisy, contaminated stream, but with probabilities, is an acceptable package to deliver. Well, we leave that one there. Maybe we'll get some comments on that. Any more questions? Then thank you very much, Gabor. And we'll move on to the next speaker, please. This is Ilkner Bezer. You could share screen.
Yes, can you hear me?
Yes, I can hear you.
Okay. And can you see my screen?
Yes, I can see it perfectly.
Okay.
I will give you a warning after 12 minutes elapse.
Okay.
And then you know that you've got 3 minutes left to wrap up, and so we can squeeze in some questions.
Okay,
Thank you very much, Ilkner.
Thank you. So my name is İlknur Gezer. I'm a postdoc in Warsaw Astronomical Observatory. So I will also talk about classification, but my work is more focused on classification of microlensing event candidates. So there were many talks about Gaia mission and Gaia science alert, so I don't want to repeat it. But briefly, the Gaia is now one of the best ongoing transient event detector. And so far, since mid-2014, almost 15,000 events is alerted. And among them, about 350 of them were alerted as microlensing event candidates. So the typical light curve of a microlensing event is symmetric and with a smooth rising and decline. So when an event is alerted, it is examined by our eyeballing team. And when it is classified as a microlensing event candidate, then we start to do follow-up observation. So we are carrying on photometric and spectroscopic follow-up observation, which Pavel talked about the spectroscopic follow-ups. Here. So, but not always the Gaia measurements are enough to build the exact shape of the microlensing light curve. But thanks to the Gaia Science Alert follow-up, we can do high cadence observations. But if it is possible to get a spectra in the beginning of the event, that ensures the early recognition of a microlensing event. But this is costly and mostly limited to the brightness. So we cannot get spectra for each candidate event. So what we here the results, yeah. So, but still we have a spectroscopic follow-up, of course. So far we have almost 100 spectra for microlensing event candidates. So they are classified based on their spectra. So now the Pavel mentioned, we classified 27 of them as a classical BE star, 25 of them young stellar object, 2 asymptotic giant branch, and 37 main seconds classified as main seconds. That means ULENS. So thanks to these spectroscopic follow-ups, now we know the main contaminants. So the main contaminants are classical BE star, young stellar object, and in some rare cases, AGB stars. Here you can see the light curve of these contaminants and the real microlensing event. This dashed line shows the time when the event is alerted. So in the rising phase, all these variable stars, outbursting variables, sorry, looks like a microlensing event. So again, we can get a spectra for early recognition, but it's not possible all the time. So we wanted to classify candidates events using archival photometry, using the machine learning method. So now we know the main contaminants, main classical BE star, young stellar object, and evolved stars, and real microlensing events. So we grouped into 4 object classes, and we collect all the known objects from the literature to build our training sample first. And then we cross-match these objects within the Gaia EDR3 and all-wise catalogs, and we took Gaia BP, RP, and G magnitudes. And from the all-wise catalog, we took 2 mass H, G, K magnitudes, and WISE 1 and WISE 2. So WISE3 and WISE4 we didn't use because they are not usable for our sources. Only 5 of our sources have usable WISE4, WISE3 and WISE4. So we didn't include for now WISE3 and WISE4. So since the brightness of an object affected by reddening, so we prefer to use the colors. So we used all the color combinations of the above passbands. So Gaia BP RP G, 2 mass HG K, and WISE1, WISE2 magnitudes, and all color combinations. So the initial training sample is consisting of 28 columns, so 28 colors we use. And machine learning is capable of handling multidimensional data. So the method that we use called supervised classification. So first we need to train the classifiers. So we use several classifiers like linear regression, k-nearest neighbors, support vector machines, naive bases, random forests, and neural networks. So we experimented all these classifiers to find the best for our needs. So our training sample contains the known object and the 28 colors. But since we are trying to classify rare and mostly faint Gaia events, not all Gaia events have all the magnitudes. So here you can see some recent microlensing event candidates. So for some of them, all 8 magnitudes are available, but for some of them, only 3 magnitudes are available. So what we did, so we tried to complete the data as much as. So we searched the other catalogs. So for example, we used Vvv GR3 to take GHK magnitudes. Again, Vista catalog we used. We took IRAC, Spitzer IRAC 3.6 micron and 4.5 micron magnitudes if they are available as a WISE1 and WISE2. WISE1 3.6 more or less and 4.5 micron, WISE2 magnitude more or less the same. So for each object, a specific training sample is created by using whatever available for this object. So if 8-band photometry available, then we use 28 colors to classify it. If 3-band photometry is available, then we use only 3 colors to classify the subject. So totally we have 344 microlensing candidates, and 168 of them have all 8-band photometry. 75 of them have only 3-band photometry. So here you can see the classification result for some recent Gaia microlensing events. Here you can see, I want to show this. Here, for example, Gaia 20 FGE, there were only 3 magnitude, but we took G and K magnitudes from Vista survey. Is also for the same for Gaia 20 FIT. And you can see here the probability. This is the BE probability, evolve, start main sequence, and young stellar object probability, and the best classifier for each object. So, for example, for this object, there are 8 magnitudes, and that means 28 colors are used. And this object, 5 magnitudes are available. That means 10 colors are used to classify this object. This is an example here. Gaia 20 ADN, 8 magnitudes are available and classified as evolved object. And we are using 90% probability as a limit. If a probability is higher than 90%, then we classify this object. Otherwise, they be classified as uncertain. So here Gaia 20 ADN classified as an evolved object. This is an example how we classified. So we tried all the models and we took the best one here, the random forest classifier, and we classified this object as evolved using the random forest classifier. And you can see the confusion matrix. This diagonal number shows that actually we are predicting very well. And this is for evolved object. Is red, it's shown with the red color. So totally we have 344 microlensing event candidates. So we classified 109 of them as a classical BE, and 26 of them have a probability higher than 90%. So the rest classified as uncertain. The same for main sequence stars, 53 of them classified as main sequence star, and 9 of them has a higher than 90% probability. The same for youngster object here and for the evolved object. I want to show this one first. So we also checked the EFAS color diagram, R minus E and R minus H alpha. So again, not all sources has a H alpha magnitude. So we cross-match our training sample and Gaia candidate events with the EFAS catalog. Here, the yellow ones, the main sequence stars, the greens, classical BE, blue ones, youngster object, and the red ones, the evolved object. And you can
That's 12 minutes, Ilkna.
Okay, that's the almost final slide. This is the Gaia 20 EDN, which was classified as evolved. And this also confirms this. This color diagram also confirms. My final slide shows the comparison between spectroscopic classification and photometric classification. Here you can see they are quite consistent. So we predict very well U-length candidates. So I think I can finish. Thank you. And I can take some questions if they have.
Thank you very much, Ilkna. That was very nice,
Thank you.
very clear. I don't see any questions in chat and no one's raised their hand. I have a question, or a couple actually.
Okay.
So if I've understood, at the moment you use no data from the light curve in your model. This is purely about the photometry of the sources.
Yes, that's true.
Yeah, because I noticed with the BE star that you used in the example, even though it's bright, it was clearly erratic and showed fluctuation before the alert. And so I wonder if there were metrics you could extract from the light curve that might help even further.
No, but if we when an event is alerted and if we can get some more points, so we can see this is a BE star from the light curve, but we want to recognize earlier. So I didn't use the light curve. I just used the archival photometry.
Yes, yes. And did you use the parallax from Gaia? I wasn't completely clear if you used it.
Yeah, that's an idea. We want to use the distance, and so we want to make like a HR diagram for our sources using the distance, but not reliable all the time. So it's in the future plans.
Okay, thank you. I see now a question from Nikos.
Can I just answer the final question? Sorry to interrupt. Just regarding the parallax, because Guy was also...
There's still one, Łukasz, sorry, there's one more question to come. And
okay, but I wanted to answer the previous question. to help you answer the
Okay.
question. Regarding the parallax, we don't trust Gaia parallax. We love Gaia, but Gaia parallaxes can be affected by microlensing, astrometric microlensing. That's why.
Okay.
That's it.
Okay.
Hello.
Nikos.
Yes.
Yeah.
Thank you for this presentation. I was just wondering, what do you mean when you say the best classifier?
So the best classifier, because for not all sources we have all the colors. So for some sources we have 10 colors, for some 12 colors. So we tried each classifier, and we get the highest accuracy, and this is the best for us, which gives the highest accuracy.
In any of the classes?
Yes.
All right. Ilkner, if you wouldn't mind stopping sharing at this point.
Yeah, sure.
And then I'll call on our next speaker, who's Roberto, to start sharing, please.
Yes, hello. How are you? I'm starting sharing.
Thank you.
Sorry. So Alexander or Roberto?
Alexander.
Okay, I think we've got your name not quite right on the
Thank you
on the program. Apologies. Okay, I'll give you a shout after 12 minutes. Thank you very much, Alexander.
Thank you. Well, my name is Alexander Servino, and I studied computer science, and currently I am a technology consultant, and recently I finished a master in data science in the University Oberta of Catalonia. And today I'm going to present my final master project, where I worked with Laura Ruiz, and we had the collaboration of Josep Manuel Carrasco and Carme Jordi from the University of Barcelona. And this project is entitled Automatic Classification of Gaia Photometric Alerts Using Spectra Data Through Machine Learning and Deep Learning. This project is focused on the Gaia Photometric Alert Catalog. This catalog provides information about photometric information about the alerts. And once a new alert is created, the related event may be classified, but as said, this is not always possible due to lack of information or discrepancies. So the main goal of this project is to implement a classifier based on deep learning or machine learning that classifies those events using the Spectra data. This Spectra data was retrieved with scraping the official Gaia Photometric Alerts website, where you can find several information about the alerts, like the alert light curve, as you can see on the bottom left figure, where each blue dot represents the blue photometry and red photometry Spectra data, as you can see on the bottom right figure. After analyzing the Gaia website, we retrieve the Gaia dataset, the photometric alerts dataset, on the 28th of April, where we found more than 1,100 observations. After this, we followed the cleansing process, where we studied the duplicate alerts that refer to the same object, and we found 3 of them. After this, we analyzed the class attribute, finding out that the most of the alerts were unclassified. And finally, we studied the comment attribute. This variable seems to be interesting because it provides additional information about an alert-related event, like its possible first classification. So after following this process, we could set the criterion for selecting our final dataset records. The first one is that the alert-related event must be referred to stellar events, not objects. The second one is that they must have their class verified on the comment attribute. This means that the Gaia system was able to give a first classification. And finally, that the related event must have enough Spectra data. So having this in mind, we could set our final data set that consisted of 4 columns: the alert name and class, and the blue photometry and red photometry Spectra data that we scraped from the website. Also, this data set was balanced and consisted of 3 types of events: ULENs, supernova, and flares. With this data set, we wanted to make a research and implement several methods. From the machine learning branch, we implemented support vector machine, decision tree, random forest, and gradient boosting. And in the case of deep learning, we wanted to try several custom, several convolutional neural networks and recurrent neural networks. In the case of the machine learning method, we wanted to make the execution with two subdatasets from the final one. One is the spectral value subdataset, where we consider its spectra value as a separated attribute. And the second one is the spectral figure subdataset, where we took the spectral image and consider each pixel of that image as a separated value. The first implemented machine learning method was decision tree. Applying this method to the spectral value subdataset reached 73% of accuracy in a little more than 0 seconds, and the 74% of supernova, the 81% of ULENS, and the 64% of flash observations were classified correctly. Moreover, applying this method to the figure subdataset reached 77% of accuracy in half of a second, and the most correctly classified class was supernova. The next method was random forest. Applying this method to the spectral value subdataset reached 87% of accuracy in 13 seconds, and also the best classified class was supernova. And applying this method to the figure subdataset reached a similar accuracy, but in almost 4 seconds. And in this case, the best classified class was ULENS. On the other hand, we also wanted to try gradient boosting. So using the spectral value dataset, we achieved an 86.5% of accuracy in a little more than 2 minutes, and the 91% of supernova, the 89% of ULENS, and the 79% of flash observation were classified correctly. Also, using the figure dataset, we reached a similar accuracy, but in this case, the best classified class was ULENS. And finally, we wanted to implement the support vector machine technique. This technique reached the higher accuracy in the machine learning area, reaching almost an 88% of accuracy in 2 seconds, and the 91% of supernova, the 84% of ULENS, and the 87% of flash observation were classified well. On the other hand, applying this method to the figure subdataset reached an 81% of accuracy in almost 10 seconds. In this case, the supernova class was the best classified. In the case of deep learning, we implemented convolutional neural networks. In this case, due to their potential for classifying images, we wanted to use the spectral images as data as an input for this method, and we created a custom grid serve function that combined several optimizers and batch sizes, using it in several architectures. We implemented the LeNet5 architecture. This architecture reached an 87% of accuracy in a little more than 1 minute. And as we can observe, the matrix evolution seemed to be good. So we consider this a suitable method for our problem. In the case of VGG, we can see a lack of convergence in the execution because the metrics seem to be stuck. So we can consider this a good method for our problem. In the case of MobileNet, we reach a good accuracy level and 78%, but in this case, the metrics didn't seem to flow as expected. So we can accept this method too. And in this behavior repeats on the ReNet 50 and ReNet 101 architectures, where we reach a good accuracy level, but we have overfitted metrics. Also, we wanted to try some custom architectures, one based in LeNet5 and another one based on VGG. So the execution of the custom LeNet5, we reached an 86% of accuracy in a little more than 6 seconds. And as we can observe, the metrics evolution is good. So we consider this a suitable method. And this is the same case as in the custom Vvv, where we find a similar accuracy in a little more than 19 seconds, and the metrics are good too. On the other hand, in the case of recurrent neural networks, we wanted to use the Spectra data as sequences because of the potential of this technique to classify this type of data. So we also implemented a grid search function that combines several number of unit layers or cell types, and we trained 80 models. And from these executions, we found out that the best model was the one with 4 GRU layers and 170 units. And this model reached almost an 88% of accuracy, and the metrics evolution was correct. Also, the time seemed to be a little high, but it is because of the architecture nature. After these first executions, we wanted to make a generalization of our data, and we went from having the first 3 classes, supernova, ULENS, and flares, and then we included an other class that provided information about other type of events or objects. So also we wanted to try the best models from the execution with the first data set and with this new data set. So comparing the random forest results, we can see that using 4 classes achieved 73% of accuracy in 45 seconds. This is lesser than using 3 classes, but it is because we have a larger data and with diverse types. So this seems to be logical. This is the same case as support vector machine, because using 4 classes achieve 69% of accuracy in 4 seconds, which is far from using 3 classes. And finally, we also ran the custom grid search function for the recurrent neural networks, and we found out that in this case, using 4 classes, the best model was the one with 4 GRU layers and 170 units. In this case, we reached a 75% of accuracy, but the metrics evolution seemed to be good too. And it is because of the same reason, because of the larger and diverse data. And as a conclusion, in this project, we have analyzed the Gaia photometric science alerts, and we have classified verified events, supernova, ULENS, and flares, and then we have made another generalization, including the other class, and we are looking forward to include more events or types just to find out the best models. Also, from the machine learning branch, we can see that the best model were support vector machine and random forest, and in the case of deep learning, we found the recurrent neural networks. As well, we consider that the most suitable model for our problem is recurrent neural networks, because though random forest and support vector machine seem to have a similar accuracy and they seem to be faster, we consider that the nature of our data and the functioning of this network seem to be more suitable. And thank you so much for listening. I would like to thank the organizer for allowing me to present today and to show our work. Thank you so much. If you have any questions.
Thank you very much, Alexander. That's really nice, really impressive. I'm really happy to see you using the Spectra and scraping them off the website. I don't see any questions, and yes, I do. Nada has a question. Would you like to ask your question, Nada?
Yes, hello. Thank you for the great presentation. I have a question regarding your classes. So under flares, are those flares on the stars or some other flares? And the second one, which also relates to these classes, is you mentioned this other class. So in other, there are all the rest types of transients or alerts. And is this really possible to use them all as one additional class because they're so different?
Yes, about the first question, The flares, we analyze the comment attribute and we retrieve the ones that indicate that they may be a flare. So we retrieve them. And after this, the other class is it is, as you mentioned, you have another type of events or objects, but we consider this a generalization of the problem just to try out the best models. So we wanted to include all of them because we wanted to analyze the results.
Okay, so for the flares, so you just used under the comments that there's a flare inside of the comment, because I know that there are in the comments it can be flare on a star or flare in a quasar or something. So maybe this is not, you know, if you're looking for flares on the stars, maybe you can specify search flare on the stars. Just
okay. We can have that in mind for our future work. We now have this project. We have an article in project, so we can take that into account. Thank you.
Okay, no problem. Thank you.
Yeah, I would strongly advise you to talk to us about the comments and how they come about, because they're fairly. It depends who's writing the comment as to whether they say flare or outburst. It's not particularly technical, and so there may be a mixture of classes that are labeled as having a flare in the comment, and so that's going to make your training set harder and more diverse than if they were all genuine flare stars. I had one very quick question as well. Do you use just the spectrum of the alerting transit, or do you use all the historic spectra as well?
We use all the spectra. We retrieve the alert, and then we retrieve all the spectra, and then we made a selection.
Okay, thank you. We're out of time, but Siegfried has a question. If you could make it very quick, Siegfried.
Can you use validated gravitational microlensing events as a separate class? Have you tried this?
Excuse me?
Can you use validated gravitational microlensing events as a separate class in your classification scheme?
Yes, we can take that into account for the article. Thank you.
But you don't have results already.
We don't have results about that now because we have only the 3 classes and the other class.
Okay.
Thank you. Nicholas, could you start sharing your screen, please? Thank you very much, Alexander.
Thank you.
How's that?
That's great. I hear you and I see your slides. I will give you a warning on 12 minutes.
Excellent. Okay. Thank you, Simon. Kia ora koutou katoa. Kona Grattenbury Aho. Greetings from Aotearoa, New Zealand. This will be a slightly different talk, I think, to other talks in this session. I'd like to share with you some developments at the University of Auckland in space systems research and how we're working towards utilizing alerts from Gaia for a particular space mission, which I would like to lead. Whoops. Okay, here we go. A little bit about myself. I was, up until fairly recently, the president of the Royal Astronomical Society of New Zealand. I am a microlenser by training, I guess. I work with the MOA collaboration in New Zealand, the Japan, New Zealand, and US collaboration we observe from the South Island of New Zealand. And the photograph behind me in the image there is of the 1.8 meter telescope at Lake Tekapo, run at the Mount John Observatory, University of Canterbury. I've done not a lot of microlensing over the last few years because what has happened in New Zealand has been a shift towards the development of space systems science and engineering. And this has culminated in the creation of a new institute at the University of Auckland, Te Pūnaha Aotea, the Auckland Space Institute. We have attracted our first main director, Guglielmo Aglietti from Surrey Space Centre. And there's a group of us who are leaders of the exec of that institute who work to develop space systems and engineering at the University of Auckland as a a new research theme of the university. And my work in that institute is largely to make sure the engineers don't run away with all the glory, to make sure that the engineers are developing and building space systems and satellites to service scientific needs, such as the ones indicated here. I'm also a member of this other center of Te Ao Marama, which attempts to answer larger questions like what is life, the emergence of life, how did it start on Earth, could we find it elsewhere in the solar system, for instance. And these two things overlap in my interests on discovering extrasolar planets and investigating surfaces of other worlds in our solar system for the existence of life. We have a number of research projects which are underway at the moment, and I'd just like to talk to you a little bit about some of those, not all of them, some of them because they relate to the development of the system that I will end my talk with. We are developing plasma propulsion for nanosatellites, so we have a couple of PhD students working with us, Felicien Ferlier and Antonella Caldarelli, working on different types of novel electric propulsion systems for small satellites. Top right there is a cold gas system, which we have replicated at the University of Auckland, but originated from the Australian National University and Stanford. We have moved on to higher energy plasmas. Shown there is an image, actually an old image from ANU SP3, which we have copied at the University of Auckland with a magnetically constrained plasma, which we are looking at using and adapting for our purposes for space propulsion of satellites. Again, this is something of an older an image, but that sort of cold gas thruster there is this small disc-like object here on the end of the vacuum chamber. And we propose that we can use these cold gas thrusters for station keeping and attitude control. This is a remarkably fast-moving field in New Zealand at the moment, and in Auckland in particular. We have gone from having no funding to develop our systems through to fairly new news. We have won about $11 million from national funding to develop these sorts of propulsion systems as part of a project led by my colleague here, Nick Long, at the University of Wellington. So this is, the gradient is very high in terms of us developing new systems and finding a whole bunch of new work for us to do. And we are proposing to try and draw these technologies together into a mission, which I'll describe shortly. With a thruster, that's all well and good. We need to be able to push ourselves from place to place throughout the solar system, or indeed adjust orbits. And so we've been looking into low delta V interplanetary trajectory optimization. And this is work which has been undertaken by Darcy Graham, a student from Nottingham, who has joined us for her PhD. And she's working with colleagues at NASA Goddard Space Flight Center on a particular type of optimization algorithm. And we are particularly interested in the interest of getting a small spacecraft to Venus, for instance. That's a longer story, more on that later, perhaps, if I've got time. I can post a link to this presentation if you want to watch Darcy talk more about that at the presentation he gave at an IAS conference middle of last year. We also have researchers working on low-cost ADACs, so attitude determination and control systems, and mechanical pointing. That is Gabor Papoti, who was working at Rocket Lab in Auckland and now works with us, developing low-cost ADACs. For those of you who are interested in space satellite systems, the ADAC system is quite an expensive piece of kit, and we think that we, for our purposes, can do as good as we need to with a much lower cost system. And so that's Gabor's problem. We told him for his master's thesis to go away and figure out how to make a $250,000 ADAC system cost a lot less. He's working on that. The interest in space systems in New Zealand has been spurred by the advent of Rocket Lab USA. Rocket Lab is a company which is the first fully privately owned and operated launch provider and is launching from New Zealand small spacecraft to orbit. That is the Electron vehicle there on the right-hand side. They are interested in pushing back the boundaries of what can be done with small satellite delivery to interplanetary space, not just low Earth orbit. So they are working with NASA on the Lunar Gateway mission, And they have aspirations for a Mars-Venus transfer as well, which is of interest to us. They have developed a platform there called the Photon, which is their third stage of their Electron rocket that is used to position their spacecraft client missions accurately in their orbits. And it has been adapted even further to be an independent instrumentation platform as well. So we're looking at using that as a means for cheaply getting into orbit with our science packages. We have been involved with a student program, the Auckland Program for Space Systems. That is a student volunteer enrichment program where students get together and design, build, and enter into a competition to fly a 1U CubeSat that's been running since 2017. It's been a highly ambitious program where we try and get the students all the way from initial design through to final design through to down select, build, test and fly within 2 years. That is a hugely aggressive timescale, and it hasn't been completely successful because everything in space, hardware design costs a lot of money and takes a lot longer than you expect. We have successfully built a satellite and have it launched on a Rocket Lab rocket back in November last year. Unfortunately, its status is unknown on orbit. We are unable to contact it. However, like anything, the first time done, it's usually not the best, and we are learning very quickly about how to correct our mistakes. So, for instance, here's just a fun image here of working with people from Rocket Lab. On the far right-hand side, you can see an engineer from Rocket Lab and my research partner, John Cater, and our student, Francis, who's looking at our satellite, which you can see on the bottom left of that image. That is the 1U CubeSat APSS-1, which was designed to do electron density measurements with a Langmuir probe. And what you can't see behind the blue box, because it is redacted because of ITER, is the dispenser from Rocket Lab. And so learning how to work with a commercial launch provider who has close ties with the US is always quite exciting. So bringing me to what I would like to be able to do in the future. We want to start using the skills that we're learning in the Institute and the talent that we're attracting to do science in space. So like I mentioned, I am particularly keen to make sure that we are utilizing these new skills and all the talent that we're attracting to do science, do astrophysics in space, and not just make it an engineering exercise. And while we've been learning how to build satellites and how we can break satellites and how we can fix them and launch them, I've always been in the background there saying, but why? What should we be doing with this newfound ability? And my interest in this work actually started about 5 years ago when I became interested in designing, building, and flying a UV telescope to do time-critical astrophysics, either in a high atmosphere or low orbit. That eventually turned into the start of a longer journey where it turned into the student volunteer program, which eventually evolved in part into a much larger program where the university committed to pursuing space science research, culminating so far in attracting our new director to take charge of the Te Puna Ha'atea, the Auckland Space Institute. So this has been a very rapid rise, and I've always been mindful of the reasons why I got into this business, and that is so that we can start building things like UV telescopes, testing them and flying them successfully. And so that is indeed what I want to do. I'm proposing to build, test and fly a simple UV telescope to react to time-critical astrophysical events, such as those being observed by Gaia or other assets, both in space and on the ground. The we here is myself, and I've mentioned before John Cater, who is my research partner who works in engineering science at the University of Auckland, and also Lukas Wojciechowski at Warsaw, because this is an idea that we have been kicking around for quite some time, and Jakub Glowacki, who works in New Zealand at the University of Victoria in Wellington. So this is an idea which we've been kicking around for quite some time. We are keen to develop it now. We were ahead of our time, I think, for the New Zealand system in terms of asking for money to design and build a satellite 5 years ago, but now we are 5 years down the path of trying, failing, succeeding, and learning. Now is the time to try apply for the funding again to do this, and that is what I'll be turning my mind to. over the next a week or so, just before the deadline for proposals. The platform that we would be using is indeterminate at this stage, but it could be, for instance, the Rocket Lab Photon third stage. So we will just build a telescope and we'll give it to Rocket Lab for them to incorporate onto their Photon third stage, and they take care of the communications and the station keeping and all of that. It could also be a balloon mission. We have another New Zealand space company called Kia Aerospace who are interested in flying balloons, high altitude balloons for scientific and industrial purposes. Thank you. Or indeed, it could be back to the good old CubeSat. So this will be much more than a 1U CubeSat. It will be a much larger instrument platform to be determined. The first step is to do an initial preliminary design, and that is what I'll be seeking funding for. So this is kind of all trying to bring it around to why we'll do this and how this will be put into action. And we will be looking to use alerts for time-critical transitory events informed by missions such as Gaia, and in particular looking at the UV spectrum, looking for those high-energy physics to learn something new about these fast transient events in the bright UV sky. Thank you very much indeed. Simon.
Thank you so much, Nick. That's really good to hear, and it's great this is ambitious and exciting. How big a telescope do you think you can go for with one of these models? Presumably they're going to be quite small.
Yeah, well, of course, it's like hi-fi equipment or any telescope. You know, you feel bigger is better, and of course, the cost goes up by the whatever is the fourth power. We're of course budget constrained because we don't have large, massive, multi-million-dollar budgets available to us initially. So I would be proposing to do a smaller system just to test out things like our ADAX, our pointing, and our communications on a balloon system first. And so I'm thinking of quite a modest aperture, maybe something that can fit inside a 1U CubeSat, so that's at least a 10 centimeter primary aperture, just as a demonstrator. And with a demonstrator in hand, we could then start looking at proposing larger missions based on the knowledge that we would acquire from that initial mission. And that is why it kind of pushes me towards doing high altitude balloon missions, because there's a chance you might get the thing back and you can repair it. To inform a larger mission, which could be a free-flying independent satellite.
Yeah. So there are two more questions. So I don't know who put their hand up first. So let's start with Milena.
Hi, thank you. That's quite exciting. I was actually wondering, the first thing was, well, what do you mean by simple telescope? But you already answered to that. I wanted to ask about the current situation with this kind of simple UV telescopes. Well, that is a niche, but there are a few ongoing projects. Could you comment on that? How advanced they are, and how special would your project be, and when you compare it to the other?
Sure. I mean, there's something to be said about. We do not have the budget or the capacity to build a system that could be another Fuse, for instance, or another UV Explorer class mission. What we're looking for is a scientific motivation. The motivation is looking for time-critical astrophysics in a band which we can't access from the ground. That means you have to go to space. And I have a personal career goal before I retire of building New Zealand's first space telescope, and I don't care if that's a Canon telephoto lens in space, or if it's a 1 meter primary. The other missions which I know of, there is Skyhopper, which is being run by Michelle Trenti in Australia. That is currently not funded yet, but they're going through the motions of applying for funding again. There is more than just a niche in UV astrophysics, because there's a number of missions, UV missions, which are going to be inoperative over the next few years. And there's going to be a gap in the UV spectrum in terms of observation capacity. We are not going to be able to do very deep observations with such a small telescope. What I am particularly interested in is creating a mission which can talk to our strengths. And our strengths are research in cold gas propulsion, strengths in mechanical deployment. That's the sort of work which Professor Aglietti brings with him from Surrey, and optics. So we have a firm in New Zealand called Kiwistar Optics. They tend to build very large mirrors and secondaries for the large telescopes around the country. And I've been bothering them for the last 5 years. They should be looking at smaller systems built in bulk. No one's going to be buying lots of UV telescopes, but I want them to start thinking about space qualifying some of their systems. Sorry, that was a long and rambling question. I'm not sure if I answered it.
Yes, I'm really sorry because there are two more questions. What I'm going to ask the questioners to do is to write their questions in chat, and if you wouldn't mind answering them in the chat, Nicholas, then we can move on to the next speaker. Thank you very much for your talk, and sorry, Katarzyna and John, but if you ask in chat, please. Thank you. Okay, I'd like the next speaker, please, Takahiro, to take control of the screen. Can you see your screen? Yes, we see your screen and we hear you.
Okay, can you see my cursor as well? Maybe not.
I see your first slide.
Okay. So
we can see your mouse, yes.
Okay. So I'm Takahiro Sumi from Osaka University. I'm going to introduce the prime focus infrared microlensing experiment. We are currently building a 1.8 meter wide field near infrared camera telescope at Sutherland at South Africa. The field of view is 1.5 square degrees. This is the first dedicated near infrared microlensing survey. And we also do the support for the Roman Space Telescope by doing the precursor and the concurrent observations. So the objective of the prime is we're going to spend 50% of the time for the microlensing exoplanet search. We're going to study the Roman planets outside of the snow line and measure the planet frequency in the galactic center. This can be compared to the planet frequency in the other stellar sparse field observed by the optical wavelengths. And also we're gonna optimize the survey field for the Roman Space Telescope and conduct a concurrent observation with Roman. So the other 50% of the telescope time will be spent for the various science which is interested in the other collaborators. So for example, using the time for the calibration for the Roman and also the TO observation of the various transient like gravitational wave, GRB, supernovae, or Gaia alert. And also we are going to do the NIR radial velocity survey for giant planets around the M dwarfs, and also the NIR transit for the M dwarfs. So here's a picture around the galactic center in the optical wavelengths. As you can see, the very near the center of the galaxy is highly obscured by the dust. But if we observe in the near infrared, we can observe more stars. So we can expect more microlensing events and exoplanets in this field. So observing this exoplanet's frequency in this region, the current optical observation is observing somewhere around this higher galactic latitude field. So the stellar density is much different from the very center of the galaxy. So we can compare the dependence of the frequency in different stellar cloudy density. So we are also doing the Raman field optimization and also conducting the simultaneous observation with Raman to measure the lens mass and also try to measure the mass function in this region. So here is the event rate map near the galactic center in the galactic latitude and longitude. Here is the galactic center and the galactic disk. This color map indicates the detection event rate map measured by the Moore collaboration in optical. As you can see, the event rate is higher near the galactic center, but we cannot see the map near the galactic disk because of the dust extinction. The prime survey is measure the event rate around this galactic center field. And then we can use this map for optimizing the Raman observation field. And also this data will be used for the study of the galactic structure in the galactic center. So we are also conduct simultaneous observation with Raman. So if we observe the microlensing events from the ground, also from the satellite, we can observe the same event from different line of sight. Then we can observe the same event with different timing of the peak and the magnification. By measuring this difference, we can measure the mass of the lens object, which is so-called the satellite parallax. The Raman and the prime combination can do the same things as demonstrated by the Spitzer telescope. So here is the one example measured by Spitzer and the ground. The black is from the ground and the red is from the Spitzer. In this case, the time difference was the 20 days because the separation between the ground, Earth and the Spitzer is longer than the distance between Raman and the ground. From the prime Raman combination, we can expect about a 4 hours difference. And this is more effective for the microlensing event with smaller Einstein radius. So we can measure such a shift in the small lensing like a free-floating planet. And this is the only way to measure the mass of the free-floating planet. Here is the hardware contribution from the different collaborators. The Osaka University and the Astrobiology Center is building the 1.8 meter telescope, and the NIR wide field camera. Osaka is funding, and Raman is providing the 4H4G detectors, and the University of Maryland is manufacturing the camera. And the Astrobiology Center is building the NIR spectrograph, and SLO is building the building. So here's a schematic of the wide field camera. The University of Maryland is building this camera by loaning the 4H4RG detectors from the Raman team. The field of view is 1.5 square degree. The temperature will be about 80 K. We will have 2 filter wheel, and we use the Arcadia electronics, which is exactly the same as which Raman is using. So in the 2 filter wheel, we have Z, Y, J, H, and 3 narrowband filters. Here we have 3 narrowbands in 1 filters, and we can choose one of them by combination with the wideband filters at the same time. So this is a figure for the spectrograph for the Doppler measurements. The science goal of this is searching for giant planets around the young stars, also the searching habitable planets around the nearby M dwarfs. The light from the telescope will be fed to the fiber by using the pick-off mirror at the prime focus, and the band is around Y and the Z band, and the resolution is 55,000. And expected accuracy of the radial velocity is about 2 meters per second. So here is the current picture of the building at Sutherland. So here is the schedule. We are still, we have manufactured a telescope, and currently on the way to the Sutherland. It is still stacked at the Kobe port because of the, we are still looking for the ship to the Sutherland. We will install around the fall of this year, and expecting fast flight this year. And we will keep observing until the Raman ending the project. So here is a summary. The PRIME is the first dedicated NIR microlensing exoplanet survey. And we are measuring the planet frequency in the galactic center. And also we measure the galactic distribution of the exoplanets. We will optimize the Raman microlensing field, conducting the simultaneous observation with Raman to measure the lens mass. And we are going to do a follow-up observation for various transients, including the Gaia alert. And we will start observing this year. Thank you.
Thank you very much. And that's really impressive. And let's see, we have a question in the chat from Pavel. Please go ahead, Pavel, with your question.
Yeah, thank you very much. Thank you, Takahiro, for your presentation. What is the expected limiting magnitude for radial velocity measurements in near infrared?
Oh,
do you know that?
Good question. I don't have an answer yet, but it should be. Sorry, I don't have an answer.
Okay, because the precision is really nice, 2 meters per second. In near infrared, I think it's quite challenging.
So this is the almost a copy of the NIR Doppler instrument for the Subaru, but slightly that is the same instrument is achieving the this 2 meters per second. So this is only the matter of the signal to noise. So this survey is only dedicated for the nearby bright object, which is expecting sufficient signal to noise. So I think this is only for the selected bright object for long-term survey.
Okay, thank you.
Thank you. Katarzyna has a question for you as well. Go ahead.
Hello, Taka. Thank you for a very interesting talk. I have a question regarding the operations of PRIME. Is it going to be follow-up mostly, or at some point are you planning to have, I don't know, alerts from near infrared for Bulge?
So the half of the time will be used for the survey, dedicated survey, and the other half will be divided to the collaborators. And then each collaborators decide what to do. But as I understand, almost all of the collaborators interested in the TOO for transient. So we're going to use some fraction of the time for the transient by virtually the sharing the time between the collaborators.
Okay, thank you very much.
Thank you again. If you wouldn't mind stopping sharing now, and I think Maria Gabriela, maybe you can start sharing once you're able to.
Okay. Share the screen.
We see your screen.
Okay. Okay, perfect. So
great. Thank you.
My name is Gabriela Navarro. I'm a PhD student at Universidad Andrés Bello in Chile and Sapienza University of Rome. So today I will talk a little bit about the first part of my PhD thesis, that is searching for microlensing events in the galactic bulge. So first of all, this is very related to the previous talk of Takahiro. So I will talk a little bit about the Vvv survey. This is a survey that is scanning the bulge and the plane with the VISTA telescope. That is a near-infrared telescope of 4 meters located in Cerro Paranal. And this telescope is scanning constantly the bulge and the plane for 10 years now. So why it's important to observe in the infrared is just because as Takahiro mentioned before, when we observed in the infrared, we can go through the dust that, for example, is very high in the galactic center, and we can detect objects. And also the nice thing of the VISTA telescope is that it is improving the previous infrared surveys, because the telescope is pretty big, right? So here you can see the difference between 2MASS and Vvv. So we are able to detect more objects in the galactic center. So this is again a way to show you what is the Vvv doing now. So I think like it's a very interesting survey because of this, and it's very useful for planning the observations of the next surveys that are going to observe in the infrared as well. So I will focus my studies in the very center of the galaxy. This is the area that I studied in the very beginning. So you can see that the extinction is pretty high there. So you cannot use aperture photometry. So I used PSF photometry for the data. And what I did basically is to construct a searching procedure to detect for microlensing events there. So I just searched for standard events. So as you can see here, there's a clear example. So what I was is analyzing 10 to the 8 sources and detecting some very nice candidates. So here are the first results that I got a couple of years ago. So you can see the pink crosses are the Vvv. It's very nice because it's complementing very well the surveys that are especially searching for these kind of objects in the galactic bulge. So another thing that we have to include in the analysis is the efficiency. The Vvv was not created for searching for microlensing events. So the sampling is irregular and it's pretty low. So for example, we are not going to detect very short timescale objects. For example, we are not searching for planets in this case, but we are searching for very massive objects or very long timescale events. So here is an efficiency plot for the different timescales and different tiles at different areas in the sky, let's say. And also we have to take into account the photometric efficiency for analyzing the complete population of microlensing events. So this is a completeness map done for Vvv especially. And you can see that, of course, we are more incomplete when observing to the galactic center. So also, if we want to analyze the complete population, we need to take into account these two efficiencies. So one of the results that we got is that if we compute the spatial distribution in the longitude axis, we see an asymmetry and we see more events towards negative longitudes. We guess that maybe this is due to the inclination of the bar. Then we analyze the timescale distribution, also corrected by the efficiency. And if we compare with some models, we see a little bit like more events in the long timescale tail. But of course, we are not sure about it because, as I mentioned before, the Vvv is not specifically for microlensing. So we are just, guessing. Then if we analyze the main time scale in different longitudes beams, we see that the main time scale decreased as we approach to the center in the longitude axis. So this is something that was discovered before, was published actually by Auckland group, but it's nice that we are detecting more or less the same trends, right? So if you are not paying attention, like this is the moment that you have to see to the screen, and here in this animation, I'm showing you the results that we got. So in the lower panel, you see the light curves of the microlensing events we found during the 5 years of observations. And in the upper panel, you can see the flashes of the microlensing events. And the brightness of the flash is related to the amplitude and the duration with the time scale. So what we can see here, we can see many things. We can see that most of the flashes are located in the galactic center, of course. And also we can see different, the observations are very irregular. So there are moments that we see many microlensing events, and there are moments that we don't detect any of them, also because the bulge is not observable during the whole year. So then I decided to extend a little bit the area. So I scanned an area in the latitude axis. So the only reason to do that also is to search for microlensing in the overlapping region with other surveys as OGLE and MOA, because we didn't know how efficient was the Vvv detecting microlensing events. So then if we compare the distribution in the latitude and longitude axis, we see an actual radio of 1.5. So it's nice because we are detecting some structures just studying the microlensing events in this area. Then another interesting thing that we try to detect is that we realize that the Vvv, the photometry of Vvv is reaching 18 magnitudes more or less in the KS band. So we detected the far disk, let's say, population. And there's many articles that are showing that that we are detecting that area. So here, for example, in this color magnitude diagram, you can see a double red clamp, and one is coming from the far disk. So what I was trying to find is microlensing events with sources in the far disk, and then trying to see the behavior of these objects with the time scale and the distribution of them. But for this, of course, as I mentioned before, we have a lot of extension in the very center, and also it's very irregular. So for example, in this case, you have a real image of the VISTA telescope, and there is an object there, a microlensing event, and you can see that the dust is like very, very severe there. So what I did is selecting areas of 2 minutes around the object. And also I studied the extinction around the object itself. So I decided to use just the population of stars that are around the object with a similar extinction. So this is for analyzing the proper motions and the color magnitude diagrams. So here you can see color magnitude diagrams in the left side and the proper motion in the right side. And what I was searching for good candidates that are, the sources are located in the, let's say, the faint red clamp of this color magnitude diagram for the stars located around the object with the same extinction. And as you can see in the plot, and there is a small bump exactly located where we expect to find this far disk bump. And in the right side, you can see the proper motions of the stars around the object. So we were searching for events with the proper motion similar that what we expect to find in the disk. So we found 20 candidates, that is the 10% of the final sample. Of course, we cannot be sure. We need more data, and now, of course, we have the VVVX that I will talk a little bit about it later. But we need to improve some data to be sure about these results. But there are very nice candidates. Also, we found among other results, we found, for example, short timescale events. That is surprising because we don't have many observations like together. But there are some moments that the VVV were observing more than once a night, and we detect some short timescale events. Then we found parallax effect in some events, and they are very interesting because we have a 10-year baseline. So we are really good detecting this kind of objects, and this is a clear one, for example. And also I wanted to mention the fact that we are not including in the final sample the incomplete events. So the results that we published already, they don't include these events, for example, that you can see in the bottom part of the presentation. So In this case, I decided to take them out because we cannot compute the time scale very well, but we found many of them as well. So, we have many interesting results, but this is not all. So the Vvv got extended for 5 more years, and now it's still working. So you can see in the red squares are the Vvv area. And the other squares that you can see in different colors are the VVVX. So now we are dealing with the extended version of the survey, and this is nice because we can study better the proper motions. The idea, the VVVX is observing for 2,000 more hours and 1,700 square degrees of area. So we are going to improve the results that we got already. So here you can see the area that the VVVX is observing in the galactic center. And this is interesting, as Takahiro mentioned in the previous talk, because this is going to be very useful for the Nancy Grace Roman Space Telescope and also for PRIME maybe. Of course, again, since VVV is not for microlensing, we cannot be very, for example, strong searching for planets, but at least we have statistics and we have an idea of how it's going to be the detection of microlensing events with these next telescopes that are coming now. So that's it. Thank you very much.
Thank you very much. Wonderful data. I'm really, really impressed. Is your movie of the microlensing sky, is it on YouTube or anywhere where I can download it and show it to students?
Yeah. We have a couple of them. They're really nice. It's a nice way to show them actually, the results. Yes.
Okay.
They're also
I would love to use that.
Yeah. Mm-hmm.
Okay. Thank you very much. Let's call on Łukasz for the question.
It's actually a question to both Gabi and Taka. This regards the connection between VVV and PRIME. Do you think there will be a chance to first of all, for PRIME to use this huge database you already have of light curves? This would speed up and purify the detections of PRIME. And then also combining the data will give you a very long timescale. So looking for extremely long events. Do you think it will be possible?
I don't know if Taka wants to say something. I can say for VVV side. Well, the nice thing is that now the VVVX is still working and we are getting more time because the spectrograph is delayed. So this is nice. So for now, we don't know when the VVVX will stop. Maybe it will be working for a couple more years. So I was thinking the same. I don't know, Taka, if I don't know if we can do something together, but I think it's pretty similar also because, for example, the field of view of the VVV also is 1.5 degrees square degrees. So I think they are pretty similar surveys. So it will be interesting to do something together.
We are very interested in because only the PRIME we have a time gap during the time zone. So the VVVX can fill the gap, and then that is very useful for catching the short anomaly in the events to catch the planet. So yes. I'm wondering when, it's very interesting in when are you going to start the survey? If there is a significant overlap in the duration of the time, we can do the same simultaneous observation.
Yeah, I'm not sure about it because now with the pandemic and everything is delayed. So I cannot tell also because the VVVX was supposed to be working until 2020. So we don't know if it's going to work for a couple of years or just a couple of months. We're not sure about it, but I think the best thing to do is to wait for PRIME to be kind of ready and then decide because we cannot be sure about it.
So for the same reason, we are very interested in to find any collaborators for the follow-up in our events.
Yes. Yes, this is very interesting to talk about. We can discuss it in a Zoom meeting for sure.
Thank you very much. I'm going to introduce Akihiko for the final talk of this session. Akihiko, you have a very short talk, if I've understood the timetable. You've only got 5 minutes, I'm afraid. So good luck and thank you.
Okay, can you see the slide?
Yes, I can.
Okay. Hello, I'm Akihiko Fukui from the University of Tokyo. So I'd like to briefly introduce the Tomoe-Gozen survey, which can be a complementary facility to the following up network for Gaia microlensing event. So Tomoe-Gozen is a wide field CMOS camera mounted on a 1.05 meter telescope at Kiso Observatory in Japan. And this camera consists of, in total, 84 CMOS sensors, which provides a field of view of 20 square degrees. And with this camera, all northern sky is surveyed with a cadence up to 3 times per night, with an exposure time of 6 seconds. And this camera has no filter, so the effective wavelength range is corresponds to the contaminant efficiency of the sensors, which is around about G plus R bands. And the regular survey started in October 2019. And the main sciences of this survey is to search for supernovae and near asteroids. But this archival data of this survey can also be useful for Gaia microlensing event follow-ups. And this map shows the locations of the follow-up telescopes for Gaia alerts. And most of the telescopes are located in the Europe, but Tomoe-Gozen is located in this region where there are few follow-up telescopes. And actually, this Tomoe-Gozen survey is very similar to the GTF survey. And actually, the performance of Tomoe-Gozen is not as good as GTF, but because they are located in different regions, it can be complementary to GTF and also this network telescopes. And in the next slides, I will show some light curves from Tomoe-Gozen. So this is the light curve of Gaia 19 DKE, which is a very long timescale event. And there are already many follow-up observations, but the Tomoe-Gozen data has some very early phase data among other follow-up observations. And this is a light curve of Gaia 19 BSY, which is likely a binary event. And so by chance, the Tomoe-Gozen archival data contains a data point which is very close to the peak where no other telescopes observed. And finally, this is a light curve of Gaia 20 FUP, which is an ongoing event. So I'm not sure if it's a true microlensing event or not, but so far no other follow-up observations has been reported to the network. And but Tomoe-Gozen has many data points, including pre-event baseline. So Tomoe-Gozen is very useful to fill in the data gaps of northern transient events, not only microlensing alerted by Gaia. But at this point, the archival data is not public. So please contact me if you are interested in this Tomoe-Gozen data. Thank you very much. So.
Thank you very, very much, and for keeping it so brief. That's brilliant. Are there any questions? I don't see any questions in chat or on the screen. So in that case, I think we thank all our speakers from this morning. It was a really impressive session. I really, really enjoyed all of your talks. Thank you very much. We've updated the schedule now because I felt it's very important to keep our break. So we'll keep our break and we'll come back at 12:15. So we'll be starting the next session 10 minutes later, which apologies for jiggering with people's timetables. So come back at 12, my time, 11:15, your time, 12:15 in 15 minutes. And I'll write that in chat as well. Thank you all very much. See you shortly.
And I would like to remind about our Wonder Me room where you can have your coffee with other people and continue the discussions.
Hi, Aaron.
Hey, Simon, how are you?
Very good. Long time no see.
Yes, indeed. I should fix this.
Aaron, please, I'd love to. The first time I met you was in the grounds of Churchill College.
I think so, yeah.
Yeah. Many years ago. 11 years ago, I guess it was 11 years ago.
Really? Wow. Yes, makes sense. Yeah.
So I don't know if you saw in chat or you heard that we're running 10 minutes behind schedule. So we'll start in 3 minutes.
Yes. Yeah.
Okay. I assume Łukasz is live capturing everything in the stream and putting it on YouTube. So you may need to restart it.
Okay. Let me know if I need to restart this.
You probably don't.
You mean sharing the screen? Restart sharing, screen sharing?
Yeah, no, that's great that you set up.
What?
I think there's nothing for us to do. I think Łukasz will just start capturing everything from Zoom and feeding it to YouTube.
Okay.
Unless he's already feeding our conversations to YouTube all the time through the breaks, which is possible.
I did something wrong here.
You started writing a new talk. Well, you've still got 2 minutes.
What is this? Oh, okay. Okay. View, present. Are you vaccinated already?
No, I'm bottom. Well, not bottom of the list,
okay.
But certainly we're just doing the over 70s now.
Oh,
frontline workers.
I got the first one.
Oh, fantastic! Congratulations.
Yeah.
According to the blinking website, there are 7 million people in the queue ahead of me. 7 million.
Hi everyone. just to let you know, hi Aaron.
Hi.
You are still being streamed on YouTube. Whatever you say, it's now public.
No problem.
Yeah. Okay. So, for logistic purposes, Aaron, you have a 30-minute talk. What I'll do is warn you when you've used 25 minutes so that you know you have 5 minutes in which to wrap up and be ready for questions.
Okay, good. And
I'd like you to start as soon as you're ready, please.
Okay, so let me start. So, hello everyone, it is a pleasure to be here. I'm going to cover two separate topics. The first one is the Large Array Survey Telescope, and the second is measuring time delay. This is a bit related, but you'll see later. Anyway, so I will start by describing our science case for building a new survey telescope, which we called LAST, the Large Array Survey Telescope. I will explain also the design considerations for this telescope and on-sky performance. Then I will switch topic and tell you about measuring time delays in systems in which the light curve is composed of 2 or more individual light curves with time delay. So the first question I would like to ask is, why do we need more sky surveys? I think that this is obvious for most of you, but let me spend 1 minute on this. We are doing very well in terms of current surveys are doing very well in terms of surveying the sky on a daytime scale. But as you know, we want to go faster, specifically on to start probing the sky on shorter time scales. And in order to do this, we need 2 things. First is we need more visits per field, and preferably not on the expense of depth and the field of view. And in order to achieve this, if you want really continuous observation, you need around the globe observations over multiple geographical positions. And in this plot, you can see them. I think this is most of the large field sky survey currently operational, and their Air Mass 2 line is shown in bold, and the dark blue is for the last telescope that we are building. And you see that the geographical position is very important for continuous observation and also for decorrelating the weather between observations. And of course, building these observatories, new observatories, is very costly, and we need to talk about cost considerations when we are doing this. Our personal science objectives includes, among others, gravitational wave follow-up. For that, we need a large field of view. And given the last point I mentioned, we really want to do it as fast as we can after the detection of the event, and therefore we would like to have good global coverage, and therefore the geographical position is important. Early detection of supernova and fast transients. Here, for example, you can see a fast transient on the right side. You can see a fast transient discovered by ZTF. This is 18 LQH. Is the bolometric light curve. The spectroscopy and the bolometric light curve strongly suggest that this event is powered by radioactive material, low mass radioactive material, like tenths of a solar mass. This is the total mass of the ejecta also. So this is very, I don't want to say unique, but it's very unusual. And we don't know what it is, but we believe that there are many more of those in the sky. They are simply very rare. The next science objective is binarity of white dwarfs and planets around white dwarfs. For this, the timescale is 15 seconds. For the transit duration, expected transit duration is 30 seconds. So this actually dictates integration time of about 15 seconds. There are also some motivation to do this because we believe we can improve ground-based precision photometry. And I will mention time delays in the second part of the talk. So design considerations. For that, I would like to define a term which I call the grasp. The grasp is simply the relative observable volume by a telescope per unit time. In Euclidean and homogeneous universe, it just tells us roughly it scales with the number of objects of some kind we can actually detect in our survey. In other words, it's a naive survey speed estimator. And if you do the math, you will find out that this grasp, or the volume per unit time, depends on linearly on the field of view, omega here, and the effective area, collecting area of the telescope is sublinear. It goes to a power of 3/4, and the thing is thing, or instrumental thing, is -3. Half, so it's actually super. Another thing you can see from this equation about 3 times the dead time. Okay, so given these considerations, you immediately understand that if you want to build a survey telescope, and given that we know that in most cases, not all of them, but in most cases, telescope cost grows faster than the collecting area of the telescope. And the conclusion is, for seeing limited survey telescope, multiple small telescopes are more cost effective compared with one large telescope. Now, this statement is sounds reasonable. However, it wasn't true until a year or two ago. And the main reason, there are several reasons for that, all of them related to technology, but I would like to mention one of them, which is very important, which is the availability of affordable large format backside illuminated low read noise CMOS detectors. And the most important part is these CMOS detectors have tiny pixels. And this is important because if you have a small telescope with a large field of view, it means that the focal length is very short, and therefore, in order to sample the seeing, you need tiny pixels. And the rough criteria here is smaller than about 4 microns. And the main point here is that with some, if you think about it a bit, it may be possible to increase the cost effectiveness of seeing limited sky surveys by order of magnitude. And this may become very important if you want to build if you want to do better than what we do today. Because right now we basically, in many aspects, we are money limited if you think about LSST, etc. So Our design is the following. It's called the LAST, the Large Array Survey Telescope. The first node that is currently under construction in Israel. I'm leading this with my colleague Sagi Ben-Ami. The first node will contain about 48 telescopes. Each telescope is 28 centimeter. Pixel scale is 1.2 arc second, and field of view of each telescope is 7.4 square degrees. The operations of this array is very flexible because the telescopes are basically separated on different mounts, and you can operate them in many different kind of modes. The two extreme ends are one single telescope of 1.9 meter telescope with field of view of 7.4 square degrees. We call this the narrow mode, and a 28 centimeter telescope with 355 square degrees. It's pretty obvious, but the wide mode is almost an order of magnitude higher grasp than the narrow mode. However, for some science cases like the precision photometry, I won't explain why, we do need the narrow mode application. In this plot, you can see the grasp as a function of wavelengths for past, present, and future systems. Ultrasat, LSST, and WFIRST are in the future, a few years in the future, and they will probably revolutionize the field. But you can see that this last system has a very nice grasp. And another interesting fact is that the hardware cost for this system is very low, is only about $1.2 million if you compare it to the other service. And this is an increase of order of magnitude increase in cost effectiveness in terms of grasp per unit cost. An amazing, a very nice feature of this system is that we can actually test the on-sky performance even before the system exists. And the reason is that all our components are off the shelf, and we are basically playing with them for the past 3 years. And we are selecting the best off-the-shelf components. And here you can see 3 examples. On the right side, you can see the signal to noise as a function of Gaia blue magnitude. Actually, it's measured using our system in dark skies. This is 15 seconds exposure, and for the median color of stars, the limit in magnitude is 19.4 in 15 seconds. And because of some data rate considerations, what we are going to do in practice is to take 20 images back to back of the same field, so 300 seconds. In 300 seconds, we go to about 21.0 5 sigma limit in magnitude. Here is just an example for an image. This is a very, very small portion of the field of view of the detector. And this is a transiting white dwarf. It's only exoplanet candidate right now. It's 18.5 magnitude object. One of our biggest challenges is the data rate from the system. With this 15 seconds exposure, the data rate is 3 gigabit per second. This is twice the LSST data rate and about a factor of 15 of ZTF. And this is very difficult if you have limited resources. So our approach to this problem is the following. We are sitting on each field, we are sitting at least for 5 minutes, so taking 20 multiplied by 15 second exposures. The dead time is negligible here. We are saving long term the individual images photometry and the co-aided images. However, the individual images are saved only temporarily for a period of about 2 months on a cyclic buffer. We are basically rewriting all our pipelines in order to enable doing this processing in real time on site and with minimal resources. And this is pretty challenging. To summarize, the first node is expected to is basically under construction now, and we expect that it will see first light in April 21, so in a few months from now. I would mention that we are looking for partners. So if you have some interest, just contact me, or if you have any questions, please contact me personally. And we are also thinking about an extension for this system, for basically extending the idea of large field of view imaging survey to spectroscopy. And right now we are just thinking about this, about some approaches to this problem. But we have a good name, which is the Large Unified Survey Telescope, or LUST. Okay, now let me, with your permission, switch topic and talk about time delays. So I would like to cover, before that, I would like to answer a specific question. So in astronomy, we have many systems in which the light curve, or it's not necessarily the light curve, but it's easy for me to talk about the light curve, is a linear combination of two separate light curves, which are identical but shifted in time. And in many cases, we cannot resolve these two light curves. Two obvious examples are lens quasars, especially if the separation is much below the seeing disk. And the second example is the reverberation mapping, in which the unresolved, the features are unresolved spectrally, basically, right? If you have a broadband synoptic survey, it's very difficult, or it's thought to be impossible to do reverberation mapping. And we developed two methods to deal with this problem, and I would like to briefly present this method to you. This is mostly done by my PhD student, Ofer Springer. And let me start. So the first question I would like to ask, or the first method, which will lead me to the first method, is that assuming that I have just a combined light from it's a light curve that is composed of two or more images, which is just linear combination of two or more light curves. Can we tell if the light curve was generated from such a process in which you have a time delay? And if so, can we measure the time delay? And the answer for this question is no. And it's actually very easy to understand why it is no. And the reason is that I can just give you a counter example. If you have a periodic light curve and you shift it in time, combine it, just take a linear combination of these two shifted in time light curves, there are infinite number of solutions for the time delays, and you cannot tell. So the criteria for success here, there are two of them. The first is that we must have a statistical model for the light curve. Without it, it's a no-go, because a priori, maybe, how do you know that the light curve is periodic, right? If the light curve is just a random noise, it won't really help you. The second criteria is that, because periodic is a specific model, but it's not enough, right? So the second criteria is that we need that the light curve will have a power on broad range of frequencies. And if we play this game, we can now, and in specifically in the case of quasars, we do have a statistical model for the light curve of quasars. Light curve of quasars are very well defined by a power law, power spectrum. Broken, maybe we don't know the index, but there are some details here, but there is a reasonably well defined statistical model. And we can ask, given this statistical model, how the power spectrum of a combined light curve will look like. And actually, this is a very trivial question. And the answer is shown here graphically and numerically. It's just another periodic function which is superimposed on the power law. Now, naively, you think about at this point, you say, okay, this is actually equivalent to doing autocorrelation function, or in other words, I can just take this model and fit it to the power spectrum using chi-square fitting or something like that. Now, we show that this is actually incorrect statistically, and it's or in other words, it's it's not using the right statistical distribution of the data, and it's basically you will bias and reduce the power of this method dramatically. So the correct, if you derive the likelihood function, it looks like this. It's not, the details here are not really important, but what is important is it is not similar to chi-square fitting. And there is a very simple reason for that. However, this is still not enough, because in frequency domain, so far we assume that the frequencies are independent, but this is never the case, just because either we have unevenly sampling, or we don't sample all the possible frequencies in nature, right? So the frequencies are always dependent on each other. So in order to solve this problem, we need to go to actually calculate, to derive this method using the full covariance. However, the full covariance include an integral which is diverging always. And but fortunately, we found some mathematical trick which allow us to solve this problem very neatly. So it's no longer a problem. And here is just a simulated example. So let me start with the upper plot. You see here in blue the simulated power spectrum of two image quasar. The expectancy value from which this power spectrum was generated is shown in red, and the best fit using this likelihood function is shown in yellow. And you see that there are, first we recover the time delay very well, although by using your eye you cannot see, it's very hard to see anything. On the bottom left, you see the delta log likelihood as a function of the time delay. The delta log likelihood is just the likelihood of the alternate hypothesis minus the null hypothesis. There is no lenses, and there is a clear minimum in the right location, so we recover the time delay. And another feature is that this method works very well for realistic, I would say, noise properties, even when the flux ratio between the images is 10%. So this is actually starting to be relevant, for example, for lens quasars, and most importantly for reverberation mapping of quasars, even using broadband observations. On the right side, at the right bottom, you can see just in the flux ratio and the total flux likelihood surface. It's not really important here. Let me switch to the second method, which is an extension of the first method. Now, in lens quasars, at least, we have more information we have more information, and this additional information is the center of light position of the images. Now, you immediately understand that the center of light position tells me something about the flux ratio between the images. So if I have the combined flux and the flux ratio, I can recover the individual likelihoods. This is shown graphically on the right top, the top right panel, which you see the purple and yellow are two images basically with time delay between them, and some flux ratio between them. The blue is the linear combination of the two light curves, and here you can see on the bottom you can see the astrometric shift, or the center of light position with noises with yellow as a function of time. And when you combine this information, you can recover the light curve, and the recovered light curve is shown in gray. And you see this, it's not surprisingly, it's doing a very good job. However, if you want to solve this properly, you need to take into account two other facts. First, we have noise in the system. And most importantly is that the quasars light curves, that these quasars light curves are highly correlated. They are generated from a red power spectrum. This means that they are highly correlated. And if we will ignore this correlation in the light curve itself, we will bias the results and severely underestimate the uncertainties. So we need to do this, and this was done. We actually wrote this likelihood function for this problem of basically the likelihood function of the position in the flux, the combined flux given the model. And you can write it analytically, but it's a bit lengthy, so I didn't just wrote it here. And I will jump into showing you some simulations. And let's start with this one, the bottom left one, which you showed again the delta log likelihood as a function of time delay. In this case, this method is sensitive both to negative and positive time delays. So you can actually, unlike the other one, we can actually tell between negative and positive time delays. And you can see a clear minima, and it's in the right simulated position basically, and it's a very good uncertainty on the parameters. This method can be used under realistic condition even for flux ratios of 5% and separations below 0.1 arcsecond, and photometric errors as high as 10%, and this is actually important for microlensing noise, which plague lens quasars. Here you can see the log likelihood surface for the log flux only method. This is the top part, okay? And when you combine it with the astrometry, basically your log likelihood surface reduces to what is shown in the bottom plot. The next step is of course combine this, use this method on real data. There are some few challenges here, but I won't discuss this right now. But this is what we are basically started to do right now, to trying to apply this methods to real data. And I will finish here, just a short summary. I try to convince you that with recent technological advances, it's possible, maybe possible, because the observatory is still not ready, but all the signs are there that it's possible to increase the cost effectiveness of survey telescope by order of magnitude. A philosophical point about this is that if this is correct, I would argue that there is no point in building large telescopes larger than, let's say, 1 meter, which are seeing limited, which is requires some community thinking, I would say. We are building the first node, and I also showed you two new methods to measure time delays in systems in which there is such phenomena. And this is of course relevant for the large survey telescope array, which we are going to apply this method given the very good sampling of data we will have. Thank you very much.
Thank you very much, Eren. So we have a question already straight away from Łukasz.
Okay, hi Eren. Just a quick question regarding the data you're going to test this. Are you thinking about, well, can you reveal what kind of data you have? Is it on quasars? And are you going to also use the astrometry from radio?
So let me start with the easier one, which is the radio. I suspect that the radio components are not following the optical components. So I'm not sure this is, so I'm not sure that you are allowed to mix optical in radio because you are not observing the same stuff. Now, I would just say that in terms of astrometric accuracy, using what we are doing right now, we can achieve, for example, for ZTF data, we can achieve two-axis combined precision of 15 milliarc second per epoch. Our systematic limit is at around 3 milliarc second. So this is enough for applying this method. Mm-hmm. It's not you need actually to run the ZTF data through this pipeline, but it's not. This is something we are planning to do. Now, related to what kind of data we can actually test this on, this is more complicated. The first thing I tried already, which is using this on Kepler data of AGNs, I didn't find anything, and it's not really surprising. Let me explain why. The AGN sample of Kepler is low redshift, and in this case, the equivalent width of the line relevant to the continuum in band continuum is below 5%. And so the flux ratio effectively is 5%. And I wouldn't expect this method, even given the Kepler data, to work on such extreme flux ratios. It will be very difficult. However, if you go to different redshift or different bands, the situation changes completely. And for example, if you redshift, if I remember correctly, redshift of 1, G band will give you something like 30% equivalent width in band. So this is excellent for this method. The ZTF data is marginal in terms of the cadence. I'm going to try this, but we'll see what happens. For the second method, ZTF data will be probably good enough, and this is the first thing we are going to try.
Okay, and how about Gaia data, of course?
Gaia data, let me...
I was going to ask the same question as Łukasz in a slightly different way, because you have a much lower cadence, but you have a very high spatial resolution.
So
and I wonder if you could break some degeneracy.
Let me, this is a super technical, there is super technical considerations here, which are, we can write these methods for unevenly spaced data. And for the first method, we did it, it's actually, what it requires from you to write the full covariance. And for the first method, we did it and actually tested it on unevenly spaced data, and it works very well. For the, and this is actually, in the case of quasars, this is actually very important, because quasars on 60-day sampling, which is let's say the mean sampling for Gaia, is quasars vary by a lot. So there is you really need to take into account all these correlations playing around with the window function. Now for the second method, we are still working on the full covariance. It's much more elaborated mathematically, and we are still working on the full covariance version. It's not ready yet. So the current answer is that it will be very difficult to apply this the second method to Gaia data. At least I don't see an easy way around this.
Okay.
You need better sampling in which you can actually interpolate the data reasonably well. Right. This can be done even with ground-based sampling of 1 day or a few days. This can be done.
Okay, understood. Mm-hmm.
Thank you very much, Aaron. I'll ask you to stop sharing your screen now so we can pass over to Mariusz.
Is it okay?
Mariusz?
Yes. Do you hear me?
We see you.
And you should see my presentation as well.
No, yes, now we see your screen.
Okay, great.
Mariusz, I'll give you a warning when you've had 12 minutes, which means there are 3 minutes left, which I would then encourage you to wrap up so you have a couple of minutes for questions.
Okay, thank you.
Thank you.
Okay, so I am more spectroscopic person than the photometric person, but I was requested by Łukasz to say a few words about the OGLE-4 transient search, which when we operate before the pandemic, which I every day spends like half an hour to 1 hour to to deliver new transient to the community. Okay, OGLE project starts 29 years ago, in 1992, I was in the primary school in this time, and there was a upgrade of the project. Project started this small telescope. The first biggest upgrade to the phase 2 was built on telescope, 1.3 meter. Project was placed from the beginning in Las Campanas Observatory. Then in 2001, there was the upgrade of the camera. In the angle to the single camera was used, then the camera was double. And from 2010, this is a huge revolution because there was the new camera used, which cover almost all focal plane of the telescope. So from the beginning, the project was led by Professor Udalski, and the primary aim of the project was looking for the specific transient microlensing events. And most of us have the microlensing background, and you know that the society is more like collaboration than the competition. And at the beginning of the 90s, there was the agreement between the groups that the groups will share the data and the events. And from 1994, Professor Udalski developed the system, early warning system, which analyzed the data real time, mostly real time. There was some delay, which is mostly caused by observer, because if we have the poor conditions, we not allow to the poor quality data go to the system, and we delay the image image reduction to waiting for the better data. Ogle is the pioneering in using the dia photometry. In this case, you need the good reference image, which is made from the combination of the images obtained in the good conditions. Then this template was used to subtract from the current image, of course, after the match, and brought them. And on this reference image, we make PSF photometer looking for the new object. And this is the very efficient way working on the very crowded field and looking for the events. Of course, after 20 years, the project not contribute only for the microlensing, but also for the stellar variability, proper motion in the region like Bulge, where Gaia is not so efficient, and also was contribute a lot to the transient science. Okay, back to the 2010, when the Ogle 4 stars. We see how it looks like the example image when we have the 32 chips. Each chips have 2K by 4K size, and with 150 seconds exposure, we are able to go to that detection limit 22 magnitudes, and pixel scales it's fit very well to the local condition in Las Campanas. It is 0.26 seconds per pixel, and the field of view it's 1.4, which cover almost all focal plane of the telescopes. Camera allow for the extended observed region a lot. So this is the primary fields observed by the Ogle 4 project. We have, of course, the Galactic Bulge, which is the biggest priority in the project, and we observe the Galactic disk, and we observe from July to March we are able to observe Magellanic region, which is in the previous phase was just concentrated on the central region of the Magellanic clouds, but now we observe the extended neighborhood, and we observe the bridge and some additional stripe as well. And in case of the transient, we just use this object, these fields, and I think from 2012, Łukasz developed the system, which is based on the previous early warning system, to looking for the transient in this Magellanic region. And it's based on the previous method. So after subtraction of the image, there was used default to looking for the new target, and this new target, when we start the pipeline, they are catch by pipeline, and there was the criterion which decided that the objects which have the Gaussian profile with on the level of 70% are shown as a candidate, and we see the product on our internal web page, and by eyeballing we select the target. Usually during the season we find over hundreds transient which is changed from 110 to 130 per season, and usually it's take me like because from 2018 I was responsible for the searching of this transient, and usually it's take me like half an hour, 1 hour daily, and if we find some new transient, we report them to the transient name server, and currently name of our transient are organized in this way that we have the prefix ogle, and we have the endings which is by the DNS server, so there is no confusion about the object, which often appears in case of the other surveys. And here you have some examples of detection of the supernovae, which is almost orphan, very easily catch, and here we have the template image. Here we have the current image, and here we have the difference, and you see how detections are clear, and when the object is abandoned in the host galaxy, it works very well. The subtraction is very nice, and even in nuclear region, which are very difficult to do the photometry there, it works very, very well. Okay, now I would like show you a few examples of detection. It's like 100 over 100 per year, but I just limit to 3, which for more important. And the first one is before Łukasz starts his pipeline. This is the V1309 Scorpio. This is the stellar merger, and we see that the light curve slowly increased, then was the rapid decrease, and there was the huge peak in brightness. And the analysis of this part before the maximum shows that the object shows the ellipsoidal variability, and the detailed analysis showed that the period became shorter and shorter, and just in some moment there was the collapse of the stars, and objects just spread the matter out. Okay, the second object I would like mention is the object found by Łukasz just before I come to Warsaw back, and this is the TDE, and we got the spectra from IPESTO, which confirmed that this object is TDE. Łukasz compares that with the other TDEs, but if you know, there is not so huge statistical samples, and there is lots of difference. But anyway, we see the very broad helium-2, and we see the very characteristic absorption, characteristic for the typical host of the TDE. Łukasz did the modeling with this TDE using the photometry from OGLE and from the Swift as well, and derived the mass of the black hole 10 to 6.2, if I will remember, and the very broad range for the disturbed stars, which was from 0.1 to 0.8. Okay, the second object was found by, I think, by Ola Hamanowicz, but the most of the follow-up work was done by myself, and we after 10 days after discovery, we got after maximum, we got our first VLT spectrum. Then we have a few more VLT spectrum, and some IPESTO, and plus SALT follow-up of this object. And this object characterized the very long rise, and after reach some peaks is not decay like a typical transient, but more or less keep the high level and start vary. And if we look on the temperature estimates from the Swift swift photometry, we see that there was very hot energetic flares, which almost 50,000 kelvins. Then it's just fell down to the 20, and it's just staying this level for the years. And these objects tend to be member of the other group, more or less in the same time. Bennett, Rockenbrot, and Yair Arkavi find the other object 2070 BGT, and now we have 5 of such objects. And Nada Ihanets, I think in Thursday she will talk about the one which was found by Gaia. Okay, this is my last slide, and you know that every single facility put in the Chile is obligated to give the 10% of the time to Chilean community, but Chilean community which have access for VLT, Gemini, and Vista, and other big telescopes like Blanco, they mostly concentrate his efforts to using this big facility. And the smaller facility was not so popular, and for example, Auger is obligated to give almost 30 nights to the Chilean National Time Allocation Committee to spread for the Chilean researchers. So, okay, and I asked my friend Juan Carlos Bamin from Universidad Autónoma if we can apply for make some kind of the mini survey, which is concentrate for constant searching for the rapid, fast transient. And we choose the field which is field of observed by Ogle, and they are located in between the Magellanic Cloud and the Galactic Plane. So the stellar density is not so high there. And additionally, there was the moments of the year when this region is available almost all night. So we have the 2 editions of this mini survey, one in February 2018 and the other one in November, December 2019. And during the first phase, we find 4 transient. This is the 15 nights in the 2018 and 15 nights in 2019. In case of the first edition, we find 4 transient. You have all of them here. And just for one them, we do the spectroscopic follow-up. This is this one, and this is the some blazars which just appear above the detection level, and then after a few days disappear. And in case of the second edition, we don't find any transient, which is quite annoying, because our nights was like in blocks of 3 nights, and we have 1-2 nights of for Ogle, which allows for the regular operation of the Ogle surveys, and we don't find in our high cadence survey. Okay, I don't mention about the time scales. In case of the first edition, we observe just 9, and in case of the second edition, we observe 28 fields, and the cadence was 36 minutes in the case of the first edition, and almost 2 hours in the case of the second edition. During the second phase, we don't find any transient, and when we back to the regular Ogle observation, we used to find some supernovae, which was very annoying. Okay, this is all what I would like to say. I just remind you that the Ogle webpage, and particularly you can go for our webpage where we publicly share our transient, and you can download I-band light curve there. Okay, thanks.
Thank you very much, Mariusz. Any questions, please, for Mariusz? Mariusz, can I ask you to stop sharing your screen now so that Susanna can take control? Thank you.
One moment.
And
I stop.
Yeah, you stopped beautifully, and Susanna can start sharing now. I see no questions, so let's move straight on to Susanna when she's ready. Thank you, Susanna. Susanna, slight change. I'm going to give you a 10-minute warning, so there's 5 minutes left to give you a bit more time to wrap up and prepare for questions. Okay, thank you.
I think it's fine. Yeah.
Yes, your slides are good and we hear you fine.
Okay, great. It has been more than 5 years since first direct detection of gravitational wave signal by LIGO and Virgo collaboration, and ongoing development of the LIGO and Virgo detectors increase our sensitivity and open new possibilities for serial detections of gravitational waves and also electromagnetic counterparts. And I would like to talk today about how Gaia fits to this novel way of observing and study universe. Oops. Sorry about that. So just to remind, when LIGO and Virgo started observations 5 years ago, 10 events, black hole mergers, and one neutron star, binary neutron star merger was observed. And so I would like to point you out to the sky localization map. So you can see that these sources are located randomly in the sky, and also the sky localization maps can have up to a few hundred square degrees. So Gaia seems to be a good tool to search for the electromagnetic counterparts as an all-sky multi-epoch survey. And so I mentioned that in one case we have the electromagnetic counterpart. It's a famous kilonova event from 2017, and it's kind of a benchmark for any transient survey now if they want to follow up this kind of events. So you can see here the sky localization map. We are actually very lucky with this event because it was at about 40 megaparsecs, and the map, the 90% probability region where the event should be found was about 30 square degrees, so very small. And here you can see the host galaxy and the event, and the optical light curve, but this one was actually observed from gamma rays to radio, so you can see the summary of all observations and the gravitational wave signal. And yeah, so the brightness at the peak was minus 15.9 magnitude in R band, so it's a bit fainter than you can be used to, for example, from observations of type 1a supernovae, and also it was very fast event. So the decline rate was more than 1 magnitude per day, which means after 10 days there was almost no signal. So we should be able to detect this by Gaia, but unfortunately Gaia was there 14 days after the event because the scanning law is fixed and we cannot change it. So we have to wait for Gaia to see this part of the sky. And even you can see in the top maps that the bottom maps that not the whole region was actually scanned these 2 weeks, but we only know that no source was detected, and that is consistent with the detection limits from other surveys. But anyway, using this event, we can study chances of future detections by Gaia, and assuming that the kilonova events have an absolute magnitude about minus 16, and if we want to reach Gaia nominal detection threshold minus 20.6, we can detect transients up to redshift 0.045. And but this is only if we're lucky and we find them close to the peak, so soon after the GW signal is detected. But in principle, because Gaia is all sky survey, we can detect about 1/4 the sky within 10 days. So of course the detection of individual events is strictly related to the localization, as the Gaia scanning law is uneven over the sky, but still it allows us to look in many places. And how, if we can detect something with Gaia, how we can use it. So Gaia gives us a very good astrometry and can help with addressing questions regarding the nature of the kilonova events. Here it was studied using VLBI radio image, where we observed a narrow relativistic jet or more isotropic outflow. So top left panel, it's actually a real image from VLBI with the inset when you have position of the event 75 days and 230 days after the GW signal. And the other three panels show the models. So the top one is a successful jet. It's called successful jet, so something very anisotropic. And two bottom panels show isotropic emission. So of course the top one is the one that fits to the data. But if we can pinpoint the detection much earlier, and do not have to wait half a year for the second observation, but we have a very accurate position of the source early, this kind of study can be done faster. In the meantime, both LIGO and Virgo were observing in run 03, which lasted about a year from April 2019 till March 2020. And you can see that there are more and more detections of the mostly black hole mergers, but also neutron star black hole and binary neutron star candidates. And all the targets are now available for the public just after the event, so we can quickly search through the Gaia regular Gaia alert stream to find the candidates, and at least 50 such transients were published via GCN network to the community. And here I'll show you one of the earliest examples from April 2019. So the top you can see the map, the sky coverage of the event, and the region of the 90% probability of the sky localization is up to 400 square degrees. So it's not easy to cover it from the ground. And also we can see the estimated distance to the source. And I picked just two of the candidates that we published. The top one, AT 2019 DDT, was, I think, actually published by other survey as a possible candidate for this event, but we found out that it was observed by Gaia actually one day before, on April the 7th, so it cannot be associated with the gravitational wave signal. And this is also the information that we can provide to the community. So when Gaia might be a few days before in that part of sky and detect something, this is also valuable information. And the bottom one, quite nice transient in this galaxy, but it revealed that it's actually type 2 supernova. And we also working now on an extension to the current algorithms used by Gaia alerts with some relaxed conditions. So we want to go a bit deeper to the nominal Gaia magnitude threshold, and also relax the requirement for the number of observed fields of view. But of course, we need to develop more sensitive filters, because then if you go deeper and you have less observations, you can get more false positives. So of course, we need to look carefully for all these artifacts that coming from Gaia, from bright stars or solar system objects. We also want to exclude the Milky Way and actually the galactic plane, as we do not expect that the gravitational wave sources detected by LIGO Virgo will be coming from center of galaxy. We did some tests on the first 2 runs, and the detection
10 minutes, Susanna.
Okay, it's the last slide. Detection possibility, it's related to the sky coverage and the Gaia scanning loss. So you might be lucky, and the Gaia was actually there when the event, the GW signal was detected, and you might also wait 100 days for the Gaia observations. But also we have some perks working with Gaia. It's all sky coverage, very accurate position, and also sometimes targets, you can observe targets relatively close to the sun. So we definitely want to be ready for the run 04 LIGO Virgo, which will start hopefully June next year, but probably we can share this kind of transients earlier to the community. Thank you.
Thank you very much. We're open for questions. Please, if you have any questions, please put them in the chat or raise your hand.
Stop sharing.
Thank you. I wondered if you wanted to say anything, Susanna, about the current detection rate that we're finding with the single field of view detector.
Yeah, it's quite high. It's kind of uncharted territory for the very fast process. There is no survey to compare.
I'm going to pass over then to Hassan. Hassan, you have quite a lot of background noise on your mic. I don't know if you can.
Okay, I shared my presentation. Is it okay?
It's okay.
Okay. Now I'm
just to let you know. Sorry, Hassan.
Yes.
I'll give you a warning after 10 minutes, and then
only
you'll have 5 minutes
okay.
left.
Okay. Yeah.
Okay.
My speech, the title of the spectroscopy and photometry of Gaia optics. I talk about an individual an object only, but it is very recent of the Gaia. Now is my colleagues also. We try to follow up observation of Gaia alerts. We have done follow-up for every times in general by using our telescopes in the Nature Observatory. We carry out photometric and spectroscopic identification of the source, and especially astrophysical research of catastrophic variables with the 3 telescopes in Turkey, Antalya. Gaia objects, very popular name is the Novacas, is one of the latest Nova alerts of Gaia. Nova has been observed in its various stage since its first note. The brightness variation range of the Nova is about 11 until the last magnitude about 21 in the differences bands, and discovery the date July 27, and also outpost date is different a little bit more August 10, the last year. The difference between the maximum and minimum brightness from the light curve of the I taken the Gaia page about for the 3 months, and this Nova is reached approximately 7 magnitudes. It can be seen. Observations in the atolls performed after the outdoors are marked with lines on the line. This line, the observational the point. The green ones in our observatory. I want to show you the big one picture. The green line, just after the outpost. So we have worked on the early stage of this object. Basically, we try to observe the spectroscopy because the nova is very bright, and also it needs the spectroscopy for the identification. Firstly, we have taken spectroscopic observation of the object with our telescopes, big one telescope. Also, we try to study the atmosphere model after the follow-up process. We report the first result in this study as a atoll the last time. From this, our data, just immediately after the outburst, the change, we saw the change in the H alpha profile in the two spectra taken a difference of 2 days, August 10 and 12. This picture, small one. Also, I will show you the big one. Just after it is action, early time, and after the 2 days, we can see very not very similar. Sorry, the change, not big, not small, but it should be changed. Maximum values of H alpha were measured in the range about 5 until about 20 angstrom from the 5 spectra at this date. We use the Grism 15. It means a very large spectral region on the objects. This change was anomalous in the nova later observation. Is important. In addition, observation of the nova were carried out on the, for example, September and November and December also. There's a rather big change after the H alpha profiles in the new observation. If you compare the August spectra, this the last observation, the profile, and also the last one, the early time, the red spectra. If you focus on the H alpha range, you can see the very large change on this profile. The change in the other lines also continuum also with the H alpha also taken some different Grism. For example, we use the Grism 7. It means the blue side. If you see, and also the continuum very change in the time about the 3 months. Also, if you focus on other lines at H alpha, beta, and OPTICON also. A great change was observed the continuum levels in the blue regions of the spectra in the data, also August. Day and day, the continuum level of the star has fallen. This change, I took the Grism 15 spectra. If you compare this blue side, you can see easily change. If you go this early time and then the down in time. Now is the time to study also the photometry side on the object. In time, we carry out photometric observation of the other objects, 101, T100, T100 nickname. We gave the 1 second exposure because very bright optics the early time, and we used the Vvv 2, and we have now don't use the any filter. We observed about 10 hours for one night. Now we will discuss the preliminary result about this photometrical data. We use many frames at the same time and at this date of the backlog. Also, we use the IRAF in general and also the PTON, we use some check anti-completion style around the object variable. Now is the want to show this light curve the firstly for us and this one also this recent NOVA light curve. We have also done periodogram. The observation were made with short pauses and the frequency intervals very short and only belong to the one night. So therefore, it is not easy to determine the period this data, but we look at the literature. We found information about the AV4. It is period in the literature 1.15 days, about 3.7 hours. So there are many some our results, but which one is the real period? So we will compare this.
10 minutes, Hassan.
Yeah, just finish, please. We will use similar period, but it's different about half an hour. So results immediately after the advanced and advanced stage of the system were examined spectroscopically. The orbital period system was found to be roughly about this value. And we will plan to make additional observations to determine the exact period of the system. And also, we are continuing the atmospheric model, study nebular phase of the NOVA. This reference and thanks and thank you from our university. Okay, thank you very much.
Thank you very much for your presentation. We have time for some questions. Do we have any questions, please? Then, Vukash has raised his hands actually in the video.
Right.
Go ahead, Vukash.
Just a quick question. Can this, I would have to look myself, but we have this Gaia spectra, BP and RP spectra. Is this line you showed, is it visible in Gaia spectrum as well? It's just out of interest. Do you see it?
No, I don't see it before from the Gaia. No, I have never.
Okay, so it's not there. We'll have to take a look because this is interesting. These narrow lines can sometimes be visible in Gaia, BP, and RP spectra, but sometimes not. Yes.
Yeah, that's right. Because we don't have any Gaia's stages of the classical nova. It's not easy, and very popular the catastrophic variables only. So it is very important for these objects. We have to work also on these objects, I think so.
Okay, thank you.
Thank you.
Thank you very much, Hassan. I'm going to ask Christoph to start sharing. If you could stop sharing, please, Hassan. Thank you.
Yes, please.
And Chris, I hope you can take control.
Okay.
Now it's okay.
We see your slide.
Okay, perfect.
And we hear you. Okay, I will give you a warning after 10 minutes. Thank you very much.
Okay, thank you. So, good afternoon, everyone. My name is Krzysztof Kamiński, and I would like to tell you, give you a little overview, a very fast, short overview of some of the projects that's been carried out using those two telescopes in the topic. The first telescope is called Roman Baranowski telescope or Poznań Spectroscopic Telescope 2, whatever you wish. It's operational since 2015, and it's equipped primarily with a spectrograph, but also capable of doing nice photometry. Currently, it's located in Arizona. And the second one is our newest, and it's not fully operational yet. It will be perhaps this year, I hope. The primary telescope is similar, 0.7 meter. Currently, it's located in Poland, but later on, I hope it will be moved to a better astroclimate. And the first topic I would like to present is a spectroscopy of eclipsing binary stars. And this is a good way of using our telescope because there are quite a few eclipsing binary stars that have been recently discovered and are relatively bright. This is a great example of such a star and where eclipses have been discovered through photometry in 2003. And after doing some spectroscopy with our telescope, we revealed an interesting feature in the cross-correlation function. You can clearly see those two lower and wider correlation peaks coming from those eclipsing components, but there is a third component clearly visible in the center. And after measuring the radial velocities and decoupling them, it turned out that it's actually not a binary, but a tertiary hierarchical system. And so we can, after this decoupling, we can clearly see the orbit of the eclipsing binary on the lower left figure, and lower right is the elliptical this time, a much longer period orbit of the tertiary component, and the barycenter of the eclipsing pair is also marked here. So it's a nice example of the project that is going on in our observatory using this telescope. Another example, another project that's been carried out for several years is monitoring of pulsating stars, particularly high mass and relatively bright pulsating stars. And here is an example of radial velocity curve for a prototype of the whole group of pulsating stars, Beta Cephei itself. And as you can see, it's nearly sinusoidal variation of radial velocity measured using cross-correlation technique with some residuals, so not exactly sinusoidal. And in this type of work, spectroscopy is especially useful for identification of which pulsation mode has been excited in the interior of the star. And here's a great example of line profile variations that we can observe in this particular star. As you can see, the line absorption line here is shifted left to right according to the radial velocity changes, but also its shape is slightly tilted to the left and to the right. And this is a clear sign of radial pulsation mode. So we can clearly confirm that this is a radial pulsator. And after removing this pulsation mode from the data, we can infer also the smaller amplitude pulsating modes in detail. Another example of a Beta Cephei type star is Delta Ceti. And here, perhaps the most interesting parameter that have been derived using our spectroscopy is its pulsation period. This star has been measured for over 100 years already. The period of pulsation have been measured that long, and you could clearly see the increase of period with time. But recently, some measurements, and our measurement is confirming it, the growth of the period is stopped. And this is interesting because for this type of stars, we believe that in most of the beta Cephei stars have these changes of pulsation period, and at least some of them might be caused by evolutionary changes. These are high mass stars, so evolution is quite fast. They are at the end of the main sequence. But this time we can see that the period growth is stopped. So we can infer from this that perhaps this star has just finished the core burning, hydrogen burning stage, and is transitioning to the left on the HR diagram, and so the period is not growing anymore and is transitioning to the shell burning stage. Another type of work that's been done on the RBT telescope is photometry of asteroids, main belt asteroid mostly. And here, as you can see on this graph, main belt asteroids are, well, the shapes and spins of those asteroids are determined quite in detail, but in most cases, the determination have been carried out only for the easiest to observe targets. So there's a significant observational bias because we know the shape and spin of mostly high amplitude and short period asteroids, which are easiest to observe. So in our project, we focus on the hardest to observe, actually, the low amplitude and the long period asteroids, to decrease this bias, observational bias, and have a better knowledge of the main belt of solar system asteroids. And this is just an example. On the bottom, you can see the light curve of a typical main belt asteroid, long period and relatively low amplitude. And on the top, you can see the model that was inferred, but not from the single light curve, but from multiple such light curves collected over several years. Another project that's been carried out is also connected with asteroids, but this time binary asteroids. There are several binary systems of asteroids known in solar system, and we also try to collect photometric data as presented here. Sometimes they present clear eclipses, sometimes the eclipses are not visible depending on the configuration, geometrical configuration, which is changing from opposition to opposition. And using data collected over many years, we can create a very detailed and accurate model of shapes, of sizes, and also of masses of those asteroids. And that allows us to determine the density and to infer what kind of materials are composing the asteroids. Is it a solid rock or a rumble pie or porous material? This is the opportunity that the binary systems are giving us. And another project that's been recently a few years ago actually started, is in collaboration with Gaia measurements of asteroids, because usually ground-based observations of asteroids are done without calibrating the data to a photometric system, or the calibration is not very accurate, and therefore Gaia measurements can be used. These are sparse measurements. We don't have a full light curves, just one point typically, but doing observations simultaneously from the ground during the Gaia measurement of a particular asteroid can give us the opportunity to calibrate the data, and then it's easier to produce an accurate model of a single asteroid. Because with relative photometry only, there is a problem with determining asteroid volumes. There are ambiguities in modeling, in 3D modeling, and with this calibration, then they can be removed. And the last topic I would like to present is so-called space safety. It's connected with Earth orbiting satellites. So again, a completely different topic than previously presented. But this is
10 minutes, Chris.
Thank you. This is of growing importance because, as we all know, the number of Earth orbiting satellites is growing, and it's growing even more recently, partly because of introduction of large scale constellations, mega constellations, so-called. Currently, there are 20,000 objects cataloged in US satellite catalog, and these are only the objects larger than 10 centimeters. There are a lot of more smaller objects. And therefore, in order to monitor the situation around the Earth, the European Union launched a consortium of space surveillance and tracking, which Poland is part of this consortium. And we are trying to monitor, especially in those areas where there are European satellites, to prevent collisions. And we try to collaborate also in the long run, in the long term, to create our own independent satellite catalog of all objects around the Earth. And this is here, the animation shows an example of satellite tracking observations, where near the center you can see the bright overexposed satellite body. And in this case, it's a rocket body. It's an upper stage of a rocket that suddenly and unexpectedly exploded after many years of free floating around the Earth. And there are some pieces that can be detected here. So this is also the way that the number of Earth satellites is growing. And the last, I would like to mention that satellite can also interfere with astronomical imaging. This is a famous example because this is very it's growing problem for large field of view observations, especially with large telescopes. So in order to help to mitigate this problem, we are creating a web service called Satellite Trail Predictor that will allow observers to generate an exact ephemeris of what kind and how many and how bright trails, satellite trails, can be expected for a particular field of view, particular location on the sky. And as you can see here, this is the prediction on the right side from our service of the trails that were recorded on the left side. And even though the orbits are not very well known and it's not super accurate, it's good enough to predict it and perhaps reschedule observations to mitigate this growing problem. And that's all from me. Thank you very much for your attention.
Thank you very much. I think there's going to be a lot of call for your satellite trail predictor over the coming years. That's impressive.
Yeah.
Do we have any questions? Yes, Łukasz, you have your hand. And Nikos too. Start with Łukasz.
Thank you, Krzysztof. That's very intriguing and inspiring, actually. I'm actually very interested in this satellite predictor. Is this website publicly available for everyone to use?
Not yet. We still have some things that we need to test. It will be launched this year, definitely, but I'm not sure at what time.
Okay, I'll be chasing you later about this. Thank you.
you mind stopping sharing now, Chris, so that Sophia can get set up? And we have a question also from Nikos.
Actually, I had the same question, so.
You need to work out how to charge for view of this. There seems to be demand.
Yeah.
I have a quick question while we're transitioning, which is in the triple system you showed us with the radial velocity curves of the two stars and then removed looking at the third component. What were the masses of the stars in that triple system?
Well, they were slightly more massive than Sun, but comparable to 1.5 solar masses.
And all three components?
All three components quite similar.
Yeah, interesting.